All right, ready to go?
You are good.
Awesome. Well, hello, everyone. Good afternoon. Welcome to this lovely Wednesday afternoon where we're going to be doing our comprehensive design review of Sundance, which is our 50-kilometer aerospace rocketry capstone project. So yeah, let's just jump right into it. First up, we got our outline. This is, again, just reference for us planning and also people doing this in the future. We'll be able to see what the sections breakdown are. But we're going to go right up into our summary of key changes from PDR. It's going to be at very high level, and this will be the rest of the presentation. We spent kind of going in detail on all these changes. These are kind of the key points to be watching out for through the rest of the presentation. The major one is the confirmation locking in of FAR as our launch site. Previously up at PDR, we were hoping to have a launch site at the Osage Nation land north of Huska. Unfortunately, that appears to have fallen through, so we have now fully committed to a launch at Friends of Amateur Rocketry, which is a field, very highly regarded field out in California in the Mojave Desert. It is a very long drive away. I think it's 22 hours, so we'll get into a bit of the logistics of that, how to get this rocket and the team over there as well, some other considerations. Playing into that as well. One of the chief ones is the redesign of the fins on both sustainer and booster of the vehicle, driven by the tower at FAR. So we're currently going to be, unfortunately, abandoning the tower concept we've been working on at PDR and moving forward using the FAR. It's the Newman 20-foot launch tower they have out there. It's designed to accommodate 4-fin rockets. And so we basically made a quick trade and said, difficulty of adding more fins, performing the analysis and validating that is going to be way easier than trying to haul out a tower out there. And with that, we did some geometry adjustments, redid our flutter analysis, and adjusted and increased those margins. Another big one, we had a bit of a diet on the vehicle. You can see these are 2 scale images here. Apologies, I'm blocking them. The vehicle has shrunk a little bit. Same diameters, obviously, that we're still working our tooling around. The vehicle's lost just over 2 feet in total height. I believe it's about a foot from both the sustainer, or maybe a little bit less than a foot from the sustainer, and most of it's from that booster, especially the recovery volume. I believe you mentioned that at the PDR. But yeah, playing that as well. A big effort was focused on kind of looking over the structures, kind of the wake of the feedback I got from PDR. So we'll go into this in detail further on, but the vehicle is now reinforced internally in a lot of sections. This is kind of like the first pass of reinforcements like 4 representing here today. And as we go through our test plan, which we'll get into near the end of the presentation, we have ideas for how to increase doing external reinforcements as well, like critical sections, to essentially validate that this vehicle is not going to shred. That ties into our risk analysis as well. And then a few other key changes are a lot of design effort has gone into the sustainer. It's specifically the avionics bay has been converged into a single volume with both the flight avionics and camera recordings equipment in the same area. Previously, there was a separate switch band kind of fill bay in the middle sustainer that held the camera equipment. We've since simplified that design and modified the sustainer to accommodate. That also helped us reduce some of our length and increased coupler caliber lengths as well. Well, again, we'll be talking about this later. And of course, the last big one is some adjustments to our sustainer burn profile. Big focus on that is reducing our overall flight loading to make sure that, again, that this vehicle is not going to shred, and also give us the highest likelihood of getting a successful flight as possible. And again, we'll talk more on that as we get to it. I guess we're going to jump right into the vehicle walkthrough. So we'll be handing this over to our design lead, Landon Votes, who will take you through the overview of the vehicle. All right, apologies, sorry. We're going to go analysis and methods first. This is similar to the PDR, going through our techniques that we're using, basically any adjustments from PDR and certain methods. There's a few new analysis studies that we're conducting and talking through those there as well, but I'll hand it over.
I'm Landon Votes. I'm the team lead for the design portion of the team. Once again, we continued with using Grass Arrow 2 and Open Rocket. Grass Arrow 2 was all of our flight simulations, however. Open Rocket was mainly used to just kind of size components in the rocket. It's easy to change and see how it affects your CG and get the interfaces and stuff to line up correctly. If there's any non-standard components, well, the whole thing is modeled in non-shape, but specifically the non-standard components, we went through and selected the materials to get the CG and wait for that specific piece, and then we were able to import that into Open Rocket. Open rocket is nice it's easy to adjust the lengths of the internal couplers, which you'll see later in the slides. We adjusted those lengths to help with the doubling effort and increasing our structural rigidity. Open rocket was also used for our booster recovery analysis, as in RAS Aero. It only tracks the sustainer. The flight simulation stops for the booster after separation. So in RAS Aero 2, though, some of the specific simulation options that are recommended by Chuck Rogers, the developer of RAS Aero, and also some other rocket designers they recommend these simulation options. The first is the Rogers modified Barrowman. It's similar to the Barrowman method, except it accounts for the length of the body tube, shifting your center of pressure and your stability calculations. The other is the fully turbulent flow. For the high Mach numbers, you will have ablation, which causes surface roughness, which basically immediately trips it to a turbulent flow, and it's a conservative assumption to assume fully turbulent the whole way. And then another one is the smooth paint option. So that is your nominal condition, smooth paint for your surface roughness. But as the rocket hits those high Mach numbers, it will ablate, and it can transition to rough camouflage paint. So if you simulate it as rough camo paint the whole way, that is kind of your lower bound, and smooth paint is kind of your upper bound. Your actual performance will be likely lie somewhere between those. And like I said, they were recommended from the previous projects and also the manual. And then finally, since the RAS Aero 2 flight profile is different than the open rocket, we sized our recovery off of the flight profile for RAS. So yeah, now moving into our static stability analysis. So the stability margin is the distance from the center of gravity to the center of pressure, and it's divided by the body diameter. So you can pretty easily adjust this by changing your fins around, and you have to have at least one stability margin for subsonic and 2 for supersonic. The majority of our flight is supersonic the whole way, so 2 is going to be our minimum. Off the rail, we are dipping down to about 4.5, and then as we gain velocity, our fins become more effective, and the stability margin increases. This large drop here is right at 4 seconds, which is our stage separation. So now we no longer have the entire length of the booster giving us stability. It's just the sustainer at this point. And the 10-second coast from 4 to 14 seconds is the ignition delay that we have programmed into our Cape 3. And then as the sustainer accelerates again, the stability does drop a little bit down to about 3. And then after burnout, it starts to climb back up again because it's now slowing down. So that's our static stability. Now moving into dynamic. So the static margin affects your dynamic response. The image on the left is our first 20 seconds of flight. This was generated from RAS Aero, and one of the kind of disadvantages of RAS Aero is that you can only select one wind velocity, and it stays the same for the whole height. So we're looking to using RocketPi to kind of run some more simulations specifically for the winds, and Jackson's going to talk about that with our Monte Carlo sims coming up. But so we start at 90 degrees coming off the rail, and if you look at the right graph, that's our angle of attack. So as soon as we leave the rail, we have an instantaneous 5-degree angle of attack. The stability of the rocket wants to reduce the angle of attack to 0, so it swings down to 87. This is our pitch attitude, so that's your angle off of vertical, or angle off of horizontal. So minus 90 is off of vertical. So we're 3 degrees off vertical, swings back up to 2, and then it kind of oscillates to about 87.5. Then you see another smaller oscillation here. That is at our booster burnout. That's where now our sustainer is continuing on its own. And then this pitch attitude, it just keeps decreasing from the effects of gravity slowing you down and angling over, and also turning into the wind. And then right at sustainer ignition, at 14 seconds, we're at about 86.5 degrees pitch attitude. So that's within our margins that we have set for our sustainer ignition. So the rocket will continue upwards after that.
Yeah, so as Landon said, we're going to jump into some Monte Carlo simulations, and we did have some updates from PDRs requested, accounting for the plus and minus 10% propulsion effects of the engines if it's either more powerful or less powerful than we expect. And then we got the far atmospheric mapping. So we actually put in latitude, longitude, and elevation to actually get the wind degree and the wind speed, as well as the air density mapped up all the way to 80,000 meters. So this is going to be really critical when we talk, where the rocket's going to land. Are we staying within a safe margin? If it's going to be too windy on the day to launch, that type of thing. So some of the initial results we had were keeping that under 30-kilometer landing radius. We're kind of seeing in between 24 to 26 for our normal distribution curves, which we'll show on the next slide. We did have simulator consistency as well. Open Rocket's still showing that 26-kilometer radius that we have, as well as included the 10% motor performance to see if we get, that fluctuation in landing distance based on that. So as Landon mentioned with Rocket Pi, in their future, we're going to the Rocket Pi library to actually take into account all the trajectory mapping with a 6 degree of freedom simulation. So essentially what this is going to show is a 3-axis chart that actually shows the parabolic trajectory of the rocket, so we can get a great idea of where it's going to land based on worst case wind loading. This will give us precise landing zones. And one of the reasons we haven't got to this yet is just because of the data gathering we have to go through. So in order to successfully do this, we're going to need spreadsheets from once the motor's finalized, and get all the grain profiles and the burn profiles from that, stuff from the avionics bay and recovery system to make sure the parachutes that we're using are correct in Rocket Pi and things of that sort. So going into our results, these are kind of what we're seeing with our 2 degree of freedom simulation currently. With a 10% motor regression, we're seeing that normal distribution peak around 26 to 28 kilometers. And then with the 10% motor progression, we're seeing that kind of drift closer to 30 kilometers, but still staying into that 26 to 28 range. So overall, this is kind of consistent with what we've been seeing. And one thing we might talk about in the future is once we get that Rocket Pi simulation done with a 6 degree of freedom simulation to see how accurate that is compared to this. Obviously, there will be some discrepancies, but what we're hoping is all the parachute geometry and stuff lowers this significantly.
Right. So hi, my name is Dev. I'm a member of the design sub-team, and I'm going to be talking about the fin analysis and the methods that we used. So we used two methods. One is by using a software called AeroFinSim, and other is by hand calcs, using a method published by Apogee Rockets in newsletter issue 615. So for AeroFinSim, it takes the geometry of our fins as an input, as well as the altitude at which the set of fins experience max Mach. And then it will use these two equations and give us a fin flutter and divergence critical Mach number, which we cannot exceed. And then for our hand calculations, it used that main equation on the right there. So we made a MathCAD file which calculates all those values, and it gives us the fin flutter Mach at the very end. A key thing to note about this equation is that 39.3 constant does depend on our fin geometry. So we recalculated that constant for both sets of fins. And then, and then we have two methods just to make sure that they validate each other and ensure that one doesn't drastically change the other. And then these results will be shown later.
My name is Owen Lee. I'll be talking briefly about our aerodynamic loading. So we utilized our Excel tool, which I talked about in the PDR, to calculate the loading across our newest rocket with 99% loading conditions at our maximum Q flight conditions. We did this for maximum Q both before and after separation to ensure we were checking all the relevant critical points of our flight. We found the 99% wind speeds for this section based on the wind power profile law, and we did that based on wind data gathered by NASA for Goldstone, California. That's what it was, which is roughly 42 miles east of our actual launch site. So we did this calculation, and the results can be seen on the right side of the screen there. And before our separation, we found that our maximum shear loading was roughly 950 newtons. Found that that after our separation, that's lowered down to approximately 360 newtons. All these calculations were done assuming that our component weights were point loads. So to remain conservative in the future, we're going to assume that the shear loading on any given component is constant and equal to the maximum shear we found through this analysis. And then we also did some analysis for our drag separation this time. And how we did this is we found the drag produced by all of the different aerodynamic surfaces of our rocket, both sustainer and booster. And then we subtracted the sustainer drag from the booster drag to find out how much force was pulling our booster away from our sustainer. We did this utilizing drag coefficients from Open Rocket, and a brief outline of our process can be seen on the left side of the screen. And that separating force came out to be roughly 750 newtons.
Yeah, so going into a lot of the aerothermal analysis, this has proved to be one of the more complex simulations we have to deal with. From PDR, we have an updated design render using the most up-to-date RAS aero simulations. This gave us higher temperatures due to longer sustained supersonic flight. A couple of the assumptions we made in the simulation was fiberglass nose cone model with no ablative to get the pure raw temperature on the surface if we didn't put something on there. This proved that the nose cone resin risked melting upwards of around 500 degrees Celsius, as well as we have conductive heat transfer to the E-bay and body tubes caused by the boundary layer. So the results we got from this, as I said, we're peaking around 500 degrees close to the nose cone tip to be exact. On the maximum heat flux, you can see this graph actually depicts the surface heat flux under the boundary layer as well as the nose cone skin temp. And then on the heat flux topic, we're talking about 4 seconds to max heat flux from sustainer ignition, as the booster is not going as fast as the sustainer. So these are the higher temperatures we're expecting, as well as 8 seconds to around the max temperature, which is a lot longer than we saw on the PDR, which is why these temperatures are climbing and thus results in an ablative. So talking with the just the distribution over the nose cone, this chart on the right's kind of showing the 5% close to the tip all the way to the shoulder at 100%. Updates from this included higher thermal loads, which kind of incorporated an aluminum tip into the top of the nose cone. The structures will talk about that more later, and obviously a fiberglass skin on the body of the nose cone. So this proves this will require an ablative coating, and what we see from this is we're above around 500 degrees, kind of right where that tip's going to start, and then all the way down to 400, and that temperature is going to keep decreasing as the rocket cools down and comes back down to the altitude. And then we range this just based on the material specifications in the code. So it's going to take a while to kind of, get the properties of the aluminum, size the aluminum tip, get the thickness we need. And aluminum also has a higher heating coefficient than, fiberglass. So we got to consider that as well, as that can conduct more heat to the nose cone, things of that nature.
Hi, my name is Chase Whitfield. I'm part of the structures sub-team, and I'll be talking a little bit about our composite airframe structural analysis. So first, I'll just give a little summary of my approach. So I made a MathCAD tool that does the analysis using classical laminate theory, or CLT. So to start out, I took our toe and epoxy properties that were given in the 54 millimeter tube we tested. And from there, I was able to get the A, B, and D stiffness matrices calculated. So after that, I then took our max external loads, NX and MX, to compute the strain and curvature in the X direction. And I took these at the maximum loading conditions under the critical sections, which we'll kind of get into later. And also add that this is just looking at a hollow tube, not with any couplers or extra thickness added to it. But going further, I used the strain and curvature found in the X direction to determine the ply level stresses in the global laminate coordinate system. That is the stress for all 5 plies that we're looking at. And also repeated this method using the experimental failure loads that we got from the 3-point bending test. And I recalculated everything in the same method. Just so we can kind of compare like the flight stresses and the failure stresses to see if our hollow tube will survive under the max expected loading. So a little bit of testing correlation and some design validation. So as I mentioned before, the initial 54 millimeter tube test kind of informed the analysis. So going forward, we're going to do feature validation with the 76 millimeter tubes. Also, the 3-point bending test revealed like local deformation failures. Also, this initial analysis kind of helped to define better testing conditions moving forward for validation. So it's not quite a full progressive failure model yet. It still needs a little bit of refinement, but it helps to inform kind of future ply orientation and like tube thickness testing moving forward. And so with that further testing and the extra refinement, it'll enhance the analysis accuracy.
Yeah, so as you've heard, a lot of our work between PDR and now was identifying some of our key risks with the rocket design and taking steps to mitigate those risks. So as a part of that, from the structure side of things, we identified several critical points where we anticipated high probability of failures. Some of these are listed here. You can see, namely, the one pictured on the left here was our parachute bay or recovery bay. That's the area above the motor, but below the bulkhead where our airframe is thinnest, carrying all of those stresses. So it leaves a lot of opportunity for large deformation and buckling. Again, our interstage coupler interfaces are of particular interest because that is what contributes to the slop along the overall length of the rocket. And there are also, in many cases, where our rocket will separate to start that recovery process. So multiple points of interest there. Again, our nose cone tip interface, as you heard with the aerothermal analysis slides, we're going to have a lot of heating here, and a lot of stress just from where that aluminum tips interfaces with our fiberglass. And then lastly, going off of what Chase covered in the previous slide, that preliminary structural analysis on our old design that you saw during PDR actually showed a negative margin of safety based on the material data from our 54 millimeter testing. And so obviously steps need to be taken to address that. Again, you know, we're going to reevaluate these analyses with the results of our 76 and 98 millimeters tests. So, you know, I'd like to reiterate this is very much preliminary, but it does help us inform these design decisions going forward. So some of the mitigation we've done on these critical points. So we have planned out a rigorous testing campaign for the 76 and 98 millimeter airframes. This will encompass our primary structural validation. So we're going to be recreating these sections of the rocket as closely as possible, testing them in the lab and validating our expected loading in that method. And then these test results will be confirmed with the hand calculation structural analysis that Chase mentioned. And we're also conducting some on the nose cone that Anna will talk about later. And then lastly, as you can see in the images on the left, these critical points can be doubled where necessary with excess coupler material. And so that's kind of our current approach. You can see the design change that we've made. And these interfaces will be sized accordingly based on those analyses and our testing results. So yeah.
All right. So now we're going to go walk through the entire vehicle. So starting at the overview of the entire Sundance rocket, the takeoff weight is, I think, a little bit heavier at 78 pounds now.
3 pounds heavier.
Yeah, 3 pounds heavier. There's still 2 stages. The booster motor is the same, the Aerotech O5500X. The sustainer motor is different, and Trey's going to talk about this later, but it's still a custom OSU made, but now the motor designation would be N2888 instead of the N3170 it was before. Still has the minimum diameter transition / interstage piece where the booster outer diameter is 104 millimeters and sustainer outer diameter is 80 millimeters. Still made out of in-house carbon fiber wound body tubes. Still with the dual deploy recovery configuration. Our apogee is around where it was last time at 188,000 feet. Our peak Mach has decreased a little bit to 4.35. Our peak thrust is the same as it was driven by the O5500 at 1,700 pounds. And then one of the biggest changes was our peak acceleration has decreased from around 50 to 33 pounds. And that is due to or not 33 pounds, 33 Gs. And that's due to the changes that Trey's going to talk about with the custom OSU motor. And we're still spending around 80 seconds of our total flight supersonic. So now our concept of operation. So the only things that have really changed on here is our peak Mach number and our altitude. So we're still going to take off from our 20-foot Newman launch tower now with 4 fins instead of 3. The booster is going to burn out at 5,000 feet after 4 seconds. And if we follow the booster, it's going to continue to climb, lose velocity, and eventually reach apogee 25 seconds in. And our drogue is going to deploy at 15,000 feet. Then our booster is going to descend until it reaches 2,000 feet. And then our main parachute will deploy from there. And then our booster lands 330 seconds later into the flight. Meanwhile, our sustainer continued to coast for 10 seconds after the booster burnout. This 10 seconds keeps us above Mach 1 the whole time, so that it's better than to drop below and shoot back up again. Also helps us with that pitch attitude I was talking about earlier, keeping that as close to variable as we can. That ignition occurs at 19,000 feet. Then our sustainer max velocity 4 seconds later reaches 4,300 feet per second at 29,000 feet. And then the sustainer has the long coast all the way up to apogee, reaching 188,000 feet 115 seconds into flight. This is where our drogue will deploy, and it will descend from 115 seconds to 700 seconds, so a long time under drogue. That's just because of how high up in the atmosphere it is. And then at 5,000 feet, our sustainer's main parachute will deploy 700 seconds into the flight, and then 250 seconds after that, or about 1,000 seconds into the whole flight, the sustainer will be on the ground.
And we'll touch on this is another change, the increase in the elevation on the sustainer main deployment altitude, and we'll talk about that a bit later.
Yeah. So now what if the sustainer doesn't ignite? What does our flight look like now? So before booster, up until booster burnout, it's the exact same. Our booster is going to climb, the booster stays the exact same. But if our sustainer doesn't ignite after 10 seconds, it's just going to continue to coast, no ignition. It's going to be heavier, so it's not going to go as high, and it didn't have that extra impulse. It reaches apogee at 34,000 feet, 43 seconds into the flight. Drogue still deploys. We're still descending from quite a while, from 43 to 250 seconds, and then our main deployment is once again at 5,000 feet. And then our landing at about half the time at 440 seconds with no sustainer ignition. All right, now avionics is gonna talk about that sustainer ignition logic.
Hi, I'm Landon Dowers. I'm the avionics lead. Talk about K3 is our flight computer that's in our sustainer. So this is what's going to be ejecting the sustainer mains, the sustainer drogue, keeping a GPS connection, sending RF signals down to the ground. But important for this slide is the K3 is going to be igniting our sustainer. And so we need to do a lot of checks to make sure the rocket isn't going off course. If the rocket had a failure and we light the sustainer, it's possible it could fly very far away where we couldn't find it, we couldn't recover it. And also, we have to be safe with this. First is our pre-launch logic. K3 has a very nice feature that it has a safety shut in it. So it can, like, with software, open the circuit and close the circuit with a safety shut to check for continuity. So we can, from a distance, check if there's continuity with the igniter without people having to be close to the rocket, which will allow increased safety because you don't want a possibility of sustainer lighting with a team out there. And then we get into the arming logic and ignition logic. The arming logic is simply a check the computer does, like a lot of these, that needs to be checked off in order for ignition to occur. And arming logic, we're really looking if the boost phase was successful. So we're checking a lot of values at 4 seconds. We're checking our minimum velocity or minimum altitude at that 4 seconds, because that's when we expect the booster to burn out. So we're checking, say, our minimum velocity is 1,500 feet. Our expected would be 2,000 feet. That's about a 25% difference. And same for altitude at 3,800 feet. That'd be the minimum that we would check off arming. We expect 5,100 feet. And additionally, we're checking our peak acceleration. This is our acceleration over the entire time when we're trying to arm, what the peak acceleration has been so far, and that would have to be 18 Gs, and our expected would be about 24.8 Gs. And if we successfully do all that, the motor will be armed, and we move into the motor ignition logic. So the motor ignition logic is looking to turn on 10 seconds after booster burnout. And so it's going to be checking things, most importantly, is our max tilt. This is what is going to determine, say, how far a rocket is landing from our launch site. And so what we have set right now, still in the works, is a maximum tilt of 10 degrees, which is going to be checking the last 2 seconds before ignition if it's been below 10 that entire time. And if so, that will be checked off. Our expected is 4.5 degrees, as we showed before. We also just do sanity checks on our velocity and altitude to make sure nothing occurred during that coast phase. A minimum velocity of 800 feet, our expected would be 1,100, and same for a minimum velocity of 15,000 feet. And our expected at that point would be 2,000. And if that's all successful, then 10 seconds after booster burnout, we'll ignite our sustainer.
All right, so now let's move into specifically our overview of the sustainer. So like I said, in the full vehicle, it's a minimum diameter carbon fiber filament wound. One of the big changes from PDR was changing from 3 fins to 4 fins. This first off was driven by the launch rail constraints at FAR, but also helps us out. The fins are kind of one of the last things you want to design on the rocket because they can affect your stability so much. So it's easy to modify them to the current design. So we reduced the span and increase the thickness on the booster slightly just to get it to match the sustainer. So that way the fins interface with the rail the whole way up. And then the reduced span also helps us in the fin flutter department by increasing our do not exceed velocity. It still has the fiberglass Von Karman in-house built nose cone as well. For recovery, we've got the dual brake, dual deploy configuration with an 18-inch drogue at apogee and a 60-inch main at 5,000 feet. For electronics, we have the K3 as our primary flight computer and the fiberglass nose cone. And then below that, still kind of in the nose cone shoulder area, are 2 run cam 4 splits in the camera bay. Now onto the motors. So propulsion is going to explain this some more, but We have the N2888 as our upper bound motor and N2877 as our lower bound motor. The bounds are pretty tight. They have, I would say, very similar performance at around Mach 4.3 to 4.2. Acceleration, peak acceleration from 32.5 to 32 flat, and then altitude difference of only 2,000 feet. The main driver behind that is their slight difference in impulse and also a very slight difference in burn time. But Trey will explain more of the why there's two different motors later on. Now going into the actual airframe. So that's the carbon fiber, the black carbon fiber tubes you see in the image on the right. Our structural weight range is 8.14 pounds to 9.24 pounds. So a pound, 1.1 pounds difference. That's just taking, what if our carbon fiber weighs 20% less than we expect? And what if it weighs 20% more? It doesn't change the total weight of the rocket too much. So that's kind of what we're looking for there. The overall length of the sustainer is 102 inches. The biggest part is the motor mount tube at 61.5. So that'll be one full mandrel from structures. And then the recovery tube is smaller at 13.75 inches. That was one of the pieces that we reduced the length of to reduce the overall aspect ratio of the rocket. Our nose cone is at a solid 24 inches. And then our motor overhang, the motor hangs off the back of the sustainer, the inner face with the interstates below. And that is one body diameter right now. So 2.99 inches or 76 millimeters. The outer diameter, including the thickness of the tubes, is 3.15 inches or 80 millimeters. The inner diameter is 2.99 inches or 76 millimeters. And then the thickness is 79 thousandths or 2 millimeters. So the OD and thickness, the inner diameter is set by the mandrel, but the OD and thickness can be subject to change depending on the manufacturing methods and the results of our testing campaign.
Okay, so for the nose cone, Ethan actually developed a manufacturing method that we plan to use and a 3D printed mold. And so we will be able to start that hopefully tomorrow. And then I've been working on the stress calculations. I used the Newtonian flow method to determine the axial and radial force that's acting throughout the nose cone. And then that was done at a flight condition of 4.34 Mach and 29,000 feet. And then I plan to do the classical laminate theory. I'm currently working on that to determine the ply number. And we plan to do testing on our fiberglass to get all of our ply properties for that. And the predicted ablative regression requires 1.5 millimeter thick coating for a factor of safety of 2.
Yeah, so backing off Anna, what she said with the nose cone, we did a CFD analysis on the nose cone using ANSYS. A couple of the input flow conditions and the simplifications we used. 2D axisymmetric flow to simplify the overall analysis so it wouldn't take weeks. A 2D mesh with over 500 surface segments to increase accuracy. Input flow conditions, we have a max dynamic pressure given by RAS Aero V2 of what this rocket's flying at, which is around Mach 4.6. The reason this Mach number is different from our updated simulation is this was run on an earlier simulation to kind of see where we were at very high Mach numbers. So the temperature, pressure, and density were all around 28,500 feet, which is around the sustainer burnout, which like earlier, this is different because this is an earlier simulation. And another big simplification is a no slip condition at the nose cone wall to not get any of those viscous effects interacting with our rocket and its boundary layer. So these results, we're showing pressure distribution over the entire rocket. We're ranging from 500,000 to 660,000 pascals with about a 15 degree oblique shock from the tip of the nose cone. Based on the horizontal axis, and then a pressure distribution for load validation and FEA. So what this means is we're working towards a full vehicle CFD analysis, and this will give us a pressure distribution over the entire rocket, so we can make further changes to either the airframe, the fins, or anything along that. And structures will get into more of that later.
All right, now kind of moving down the rocket, the next piece is the sustainer recovery tube. So this houses the upper part houses our main and the lower part houses our drogue. The black part you see is 18.5 inches of carbon fiber. It's joined to the nose cone with a around 10-inch coupler, and then joined to the sustainer motor mount tube below it with an 8.98-inch coupler. The parachute bulkhead is right here in the middle, so it divides them, and there's an eye bolt on both sides, so the recovery is attached to the same spot there. And then the shear line or the shear pins are below the shear line / the joint at each interface. So for this, the motor mount tube would slide up here, and then the shear pins would be this section. This is the sliding part of the coupler, and this part of the coupler is also 1.5 times the body diameter on both the sustainer and the booster. This gives you a good interface to have good. If your tolerances are good, you'll have a minimize the slop there, and if you go longer, you're increasing the overall aspect ratio of your airframe and also the chance that it won't actually separate because there's too much, it's too tight or there's too much friction there. So 1.5 is a kind of a happy medium there. And then this tube generated positive margin of safety for all the plies at critical points under max expected loading. That's because of the additional coupler and reinforcements that we did add in that area. And we'll see that later. All right, now moving on further down the rocket, I'll be sustainer motor mount tube. So that's the very long 61.4 inch carbon fiber piece. It is joined to the forward airframe with the same 8.98 inch coupler. And then it's joined to the interstage with the motor case. That is this blue piece right here that's hanging out 3 inches. It's interfaces with the interstage below that. Also living in this tube is the drogue parachute and our custom motor retainer. All the bulkheads on the entire rocket are epoxied in place, and then our custom retainer will basically, there's the forward closure on the motor, on the actual motor, and then we have a bolt that goes through there, threads into a slot on the top of the retainer, and we just tighten that until it bond or fully interfaces with our epoxied in place retainer. And this has to be custom because the commercial retainers you buy have a center threaded piece, and we'll have to do a slight offset to accommodate the head end ignition. And then the shear pin connection is also below the shear line on this one as well.
So looking at our sustainer fins, besides the main change from going from 3 to 4 fins, the biggest change we made is going from double wedge to hexagonal cross section. And this is mainly due to, we changed in the simulations, we changed it to hexagonal cross section, and it didn't really have that big of a performance difference, as well as hexagonal fins are easier to manufacture and more robust. So we decided to switch to that. And also they're highly swept, and this is needed as the sustainer is going to go Mach 4.3. So a highly swept fin will help with performance in that area. And the current plans to construct these fins is going to be out of 6061 aluminum with epoxy fillets. And so using this material and these geometry, we can conduct fin flutter analysis using the methods previously discussed. And the critical Mach number that we get from AeroFinSim is about 9.5, and by hand calculation is about 12.1. This is about a 2.5 difference, which is quite significant. However, the average factor of safety that we get is a 2.5, which is ideal. So it makes this a good sustainer fin design.
All right, now moving kind of back up the rocket towards the sustainer interior. So this is from our on shape, but so I've made the exterior body tubes, the black carbon fiber tubes, transparent. The main changes are that so this is the rocket fully assembled. You'll see that this is our motor retainer. The dark blue is the motor, the light blue is the motor retainer. Then that's our first kind of reinforcement, and then our main coupler, and then our nose cone coupler. And you'll notice that they interface the whole way down the rocket. That kind of gives us a sandwich of joints from the exterior interfaces as well as the interior interfaces, kind of doubling up that area to help us fight that bending moment. And then the bottom is kind of how it will separate. So the forward side of this coupler is fixed in place, and it originally only went to about here, but then we extended it up to meet the interface here from the nose cone. And both of these interfaces are, once again, 1.5 times the body diameter.
So hi, my name's Ben, and I wanted to talk about the redesign of our sustainer avionics in Gamma Bay. So one of the big changes we made is we went away from our fiberglass bulkheads and actually moved to an aluminum construction, as well as aluminum standoffs to help distribute our load. The attachment point has now been moved to be riveted into the nose cone. So we've moved that joint higher away from the lower coupler edge, as well as we incorporated redundant separation charges in this design to ensure appropriate separation. And then our camera system, which we moved up, has a dual camera system with individual LiPos that both have dedicated BECs. And then we also have mounts in there to adjust the camera angle to make sure that fits flush inside of that coupler. And then all of this is activated via an Adafruit latching relay, which we'll discuss that circuit a little bit later. So kind of an overview of the design, and this design, we actually base it on the Mesos rocket in kind of pulling some inspiration from that. So on this lower end here, we have our 2 separation charges as well as our eye bolt. That's going to be our attachment point for our recovery system. That's connected to an aluminum bulkhead that is then transitioned into 3 aluminum standoffs. And then at which point those are connected to our larger bulkhead that's going to house those riveted joints. That is going to go not only through your 54 mm body tube, but as well as the 76 mm coupler and the nose cone as well. So that's going to make that connection really strong. And then that picture on the right kind of shows the internal layout for the Adafruit latching relay, and as well as showcasing one of the circuits with the RunCam camera, a LiPo battery, and a BEC.
All right, now specifically talking about the sustainer recovery volume. So our sustainer main parachute is the 60-inch Irish Ultra Compact from Free Shoots. They're a trusted brand. We used them before as part of the Rocket Club. They're great. Its packing volume is 52.3 cubic inches, and inside that coupler that it's going to stay in the sustainer airframe, that equates to a packing length of 8.3. It has a CD of 2.2, which is great. To kind of squeeze down the volume and mass that parachute needs to take up. If our sustainer is lit, the descent velocity under main is 20 feet per second, and then unlit with a little bit heavier, it's 27 feet per second. And then now our drogue parachute, so the one that comes out of Apogee, is an 18-inch compact elliptical, also from 30 Shoots. Its packing volume is a lot smaller at 8.92 inches cubed, and then its packing length, it takes up less than an inch and a half of space in the sustainer coupler bay that we have set for it. Its drag coefficient is a little lower. It helps us because it kind of helps us fall a little faster from Apogee, so we're not just coasting forever. And then the lower CD equates to a lower drag force to help us get down there. Our descent velocity, if we're lit, is 80 feet per second, and then unlit is 110 feet per second. And disclaimer on those velocities, those are from Brass Arrow, and the only drag that it accounts for is the drag from the parachute itself. It does not account for the drag like the tumbling separated rocket body. So the actual descent velocities will be slower than what the simulation will tell you. And then down here is kind of just a diagram of how it is. So we have our sustainer motor and then our drogue volume below that. These are the separation charges that will separate. It'll separate right there, and then the main and the nose cone will stay connected to each other until we hit that 5,000 feet, where then these separation charges will blow and kind of blow the top of the nose cone out and pull the main parachute out with it. And the recovery harness, we have shock cord that goes from this eye bolt here to here, and then it connects through the main parachute to up there. So everything is hooked together and hanging from the parachutes as it comes down.
Also worth mentioning here, we've got the drogue charge separation wiring running from the K down to this main volume, as well as the motor wiring, which also runs to the drogue volume. I think it's mentioned here in the diagram, but those will have breakpoints there. So when the separation event does occur, those wires are not trying to fight back and hold the rocket together. So
yeah, we've used this technique on our previous 2-stage rockets. We basically butt 2 XC30s up together, and they just separate right at that joint. And it's okay that the wires are going through points where it separates, because all this will be connected when the motor connects, and then we don't need that wire to be connected anymore. So we can break here, and then this we don't need this wire anymore after so this is the motor wiring, and then our drogue separation wiring is contained in the main volume. That stays together. After that separates, then our main separation wiring is right there, so it separates there as well. Moving on to the next slide.
Yeah.
That'd be great.
I'm Trey. I'm going to be talking a little bit more about our sustainer motor. Kind of an overview. It's going to be a 76 mm custom solid rocket motor with a monolithic base finished steel geometry for controlled burn. It's going to be right around 1,100 Newton seconds of impulse and a peak thrust of right around 800 pound force. This will be housed in a Loki 76 13,000 casing with a rating of around 3,000 psi burst pressure. A little bit more about the manufacturing and material selections. We will be using a glass phenolic nozzle. It's an RCS commercial nozzle, which we chose the commercial route for simplicity. We have a custom Aerotech style threaded Ford closure, which we will integrate the head end ignition as the ignition system into that. We're utilizing a pourable propellant formulation, which was prioritized for ease of casting. It's also worth mentioning that we will use phenolic liner bonding as the 76 13,000 case exceeds the standard liner sizes. A little bit more about our head end ignition system. So it's an internal head end ignition system. So this will improve the aerodynamics. And it's going to be integrated into the Ford closure, so it will be compact and efficient. A little bit more about the compound selection. So original plan that we discussed in PDR was using copper thermite, but due to safety concerns of not having enough time to test it and also not having testing facilities within the timeline, we switched our approach to using propellant shavings. So the advantage of this is that it's going to be safer and easier to integrate. But a disadvantage is that we cannot fully verify ignition at the specified altitude. We can only do ground testing. A little bit more about our propellant selection. So considerations that we discussed in PDR was using 90 micron AP, which we ordered, but due to supply issues, we likely will not be able to use that. So we are switching to using our baseline CS, is what we call it, formulation. It's already been characterized in-house, but it will have some slight adjustments for pourability. Use a 400 and 200 micron AP bimodal base. Still uses oxamide as a burn rate suppressant. And we're able to optimize the motor geometry, which was a big thing to reduce peak acceleration from around 50 Gs to 33 Gs. And it's been a question is why not use a propellant that has characterization information already provided online. Recharacterization would be required anyway because there's inherently ingredient quality variations, and also there are safety risks associated with that. The ingredients that we use in our propellants don't require super high levels of PPE as compared to the volatile ingredients that you'd see in other propellants. So it's been mentioned the performance bounding of our motor design. So I'll explain a little bit more about what that is. So since we were originally planning to utilize 90 micron AP and we can't do that, we utilize this bounding approach. So our baseline propellant that we've already characterized needs to be refined for improved pourability. So to make sure that our final design is suitable for the loading and things like that, we define two bounds to guide our motor development. We have our lower bound, which is our CS propellant. It's in-house, fully characterized, but it's not pourable. And then our upper bound is a Joseph propellant called Risky Batman, which has been characterized online, and it's highly pourable and would be extremely similar to what we would have used if we used 90 micron AP, but it's not intended for use. So our final formulation will fall in between these two bounds, both in terms of pourability. So it will be more pourable than our CS propellant, but not necessarily quite as pourable as Risky Batman. And also in terms of performance, we're able to optimize geometries for both the upper bound and lower bound, which I will talk about here in just a second, so that we know our performance of our final motor will fall between those two bounds. And like I said, we optimized a geometry for both of these propellants, one optimized for the CS and one optimized for Risky Batman. And we concluded that there are no major manufacturing differences between the designs and that we would be able to use the same materials and same manufacturing techniques.
All right, so now that we're done with the sustainer, we're going to move into the booster overview. So still the minimum, same carbon tubes. We did reduce the 4 fins. We reduced their span. That helped us with the flutter velocity. And on these, we also slightly increased the thickness. On top of our boosters, our 6061 T6 aluminum interstage that provides the connection point between the two stages. The recovery is the same dual brake to employ as the sustainer. There's a larger drogue and larger main, just because of the increased mass of the booster. The electronics, there's one RunCam 4 for our booster footage, and then two telemetrons for recovery, which are some other commercial flight computers. The motor for this booster is still the Aerotech OPDI 100X with 21,384 Newton-second fin pulse, 4-second burn time. That's going to push the booster, the whole booster and sustainer stack at separation is Mach 1.7, peak acceleration of 23.2 Gs, and altitude of 14,800 feet. For the airframe, we did the same positive and negative 20% carbon fiber analysis, and that put us at kind of a similar difference at 10.9 to 12.3, a little bit more variance there just because there's more carbon on it. The booster's length is 94 inches, with the largest segment being the aft booster, or like the motor mount, it's 63.5 or 63.3 inches. The forward booster, this would be like kind of the recovery volume, would be 20.8 inches. And then our inner stage, the part that's actually visible to the air is 1.5 inches long. And then our motor overhang is 4.4 inches. The nominal dimensions, like I said earlier, are an OD of 4.016, an ID of 3.874, and still the same thickness of 79 thousandths or 2 millimeters. And kind of the same disclaimer that the OD and thickness are subject to change following our manufacturing and testing campaign. Yeah, Josh, you got the interstage.
So taking a look at our interstage, there's been very few design changes between PDR and CDR. Our material is still 6061 T6 aluminum, just for availability, as mentioned previously. It's been important to note here that this aluminum construction allows us to get some really tight tolerances around that interstage to sustainer connection, since it is interfacing with the sustainer motor. You see an aluminum to aluminum interface there. Yes, thank you. So another small design change is just that we added a sloped aft side to more smoothly transition the stresses between the airframes. But other than that, it's remained the same. It will still be drag separated and still transition from 98 to 76 millimeters. We've done some preliminary FEA on this joint to simulate both the compressive loading at max Q on the, max Q on the boost stage, as well as a 9-degree angle of attack gust loading, which is extremely conservative. I think our 99% wind analysis only set us around somewhere like 4.6 degrees. So this preliminary FEA aligns very well with the compressive hand calculations that were completed, but we're still looking to refine this study. I think as a team, collectively, we don't have a ton of in-depth experience with FEA, and so we're still looking to improve this, get more accurate results. But yeah, we're very confident in this part of the design.
All right, kind of moving down through the booster again, our recovery tubes. They're 9.2 inches and 11.6 from the carbon fiber, the two airframes you see on the left. They're stiffened by that extra coupler material to prevent buckling. There's parachute bulkheads on each side of the coupler, epoxied in place. And then this specific area was identified as a critical point, so we increased the thickness by kind of doubling up these couplers the whole way. You can't see it too well, but like there is a coupler that this parachute is fully interfaced in that runs up to there. And that orange cylinder you see is the main parachute. Now, moving further down the rocket is the booster motor mount. So this is by far the longest structural piece of the rocket at 67.3 inches of carbon fiber. It's joined to the forward part of the booster airframe with an 11.6-inch coupler. And inside this volume, inside this tube and coupler, there is the drogue parachute as well as a commercial motor retainer. It's aluminum. You can buy them from Aeropack. And we can use the commercial on this since it's a center. We can thread straight into the center. There's also same with the epoxy joint bulkheads, and that aluminum retainer will be epoxied in place as well.
Looking at our booster fins, they're similar to our sustainer fins in most aspects, 4 swept fins and an hexagonal cross section, except two major ones. It's not as swept as well as the span is higher, and it's not swept as much as the booster only goes 1.7 Mach, so it doesn't need to perform at higher Machs as well. And then this provides greater stability. The higher span also provides greater stability, which we will need at launch. Currently, the plans are to have epoxy fillets, and the material choice isn't hammered down just yet. We have quite a bit of freedom as the booster is not going as fast. So the two materials we were looking at for this CDR is 6061 aluminum and an in-house carbon fiber. So for the thin flutter critical Mach number for aluminum, Aerofin gives about 5.5 and hand calculations gives about 5.1. These are pretty close. And then the average factor of safety is 3, and that's really good. And for in-house carbon fiber, it's the Mach number is 1. So this material just out of the
Margin of safety.
margins. Yeah.
And I would say this is also for that composite analysis, very conservative numbers we're using for that. But still definitely there's a lot of extra uncertainty to composites. We have used composite fins on a very similar vehicle overall to what the booster is going to be on Arachne, and they perform very well. And so this is something we're still kind of considering, leaning towards the aluminum fins right now. Because we're already to prove that with the sustainer, it doesn't seem like too much additional scope to basically do double that work for the booster. We do also already have the previous flat plate experience with the composite fins as well. So again, just looking into that, and that will be hammered out probably in the next few days. But yeah.
Now kind of the same with the booster interior. So this is again with the carbon fiber tubes made transparent. So this first section is our custom or the commercial motor retainer, and then the coupler slides and meets up with that, and then the second coupler also meets up with the top of the first coupler, and then that top coupler meets with the interstage. So it's a full continuous double wall thickness stack there, and then at when it's fully separated, the parachutes aren't here, but this is where the drogue would be, and this is where the main would be. This is still the 1.5 times the diameter of the booster for the sliding interface on both of those couplers. And now talking about the recovery volume. So the booster parachute has a 6-foot ultra parachute. Again, for chutes, the packing length is about 6 inches, and it still has a CD of 2.2. The descent velocity under there is still 20 feet per second. There's only one because the booster is definitely going to light. So if it doesn't, it's not going anywhere. So then the booster drogue has a 30-inch compact elliptical parachute. So bigger drogue, and then the descent velocity under drogue is 60 feet per second. And part of the reason why that descent velocity is lower than the sustainer is that it's such a large parachute coming out can really put a big snatch load. So we kind of want to ease the transition between the drogue and main parachute on this.
Do an overview of our booster avionics and camera bay and our so the main goals for this avionics bay is to light our ejection charges for our booster drogue, booster main, and also to capture some great footage during the booster descent. So first, for the ejection charges, we're using 2 telemetrums. These are very tested, used probably regularly, lots of heritage. So these are very trusted devices, each of which have two paths to ejection charges. I showed the ejection charges in the top and bottom here. These are ejection charge developed by Jim Jarvis for high altitude rocketry. So there's a lot of heritage in that. Those have been used in the Arachne rocket. These are devices we believe are very reliable.
And worth mentioning real quick, these are also the same that are used on sustainer. I think we forgot to mention that. I could keep going.
So these telemetrics, they're currently connected to 2 120 milliamp LiPos. We recently decided that's probably too small. We're going to increase that. Those last about an hour. We're usually looking to get about 2 hours on those telemetrums just for margin. And there's 2 screw switches to activate those 2 telemetrums. So we'd have external holes to be able to power those before we leave the rocket. Because this bay is in a carbon fiber tube, there's no way to get RF transmission in and out. So as of now, we're not planning on using the telemetrums to connect to our ground site. That's going to be purely a CADE capability. Next to our camera bay, that's the cyan bay below, we have 2 run cams on here. We're trying to test out systems for future research, and one of which is an accelerometer-based camera system. So we're wanting to activate a camera based on accelerometer data. And this is obviously going to mean we won't catch the first, maybe second of flight. But it is a system that's completely on its own. We don't need to talk to it. We don't need to connect to it. And it'll be able to turn on that camera. And we're currently looking into how we can get that acceleration to not like activate when we touch it, but will activate when you have that sustained acceleration during flight. And then on the other side, we have a simple camera system that's just flip a switch before we leave the rocket. These both have 720 milliamp LiPos, so that camera would last approximately 2.5 hours. And so it's very likely that that camera is not going to run out of juice. But we have two different systems here to get the reliability high on our cameras.
Yeah, so booster motor, pretty straightforward. We're using 98 millimeter diameter commercial motor known as the Aerotech 05500X. The impulse of 21,384 Newton seconds and a peak thrust of 1,698 pound force. Yeah, it's a reliable and tested motor. The Rocketry Club has flown it several times, so it's a reliable and simple motor for us to use.
Right. And so with all out of the way, quick walkthrough of where we're at through the entire vehicle. Now, the big question, how do we make this thing real? And so that's what we're going to start talking about here in this next section. So the project manufacturing test schedule. So we're going to start with the overall project Gantt chart. This is kind of a simplified version. I mentioned during PDR that we're using Notion as our primary project software, tracking like tasks and projects at kind of like very detailed, like nitty-gritty level, like going down. I think we're up to like 90, 100 tickets like tracked on that. But this is essentially like a simplified version of what we've got there with our critical milestones before flight. So right now we're at CDR right here. It's a nice mapped way, like almost halfway or just before halfway through the semester. And then leading up to flight, we've got two more critical milestones. It's going to be the test readiness review and the mission readiness review. And so essentially, to talk through this real quick, in the wake of CDR, we're starting to get ungated, and we'll have a bit more information about this following in the next few slides. But we're basically ready to move full steam ahead into full-on manufacturing and testing of the entire airframe, avionics, and then there's already a lot of work done on propulsion, but working towards those full-scale test fires. They're already starting doing same diameter test fires, the 76 millimeter with the formulation. But the work that needs to be done there is to increase the portability and get the final flight-like formulation and test that in a fully integrated assembly with the head and ignition system. So essentially, the work that we're going in over the next few weeks is to conduct all these tests, feed them back into the analysis we've discussed so far. That's one of the really critical things that we've been working on throughout the entire project, is making sure that, especially with like our structural tools and all of our flight profile tools, that as soon as we get this data, we're able to like roll it in and incorporate it as fast as possible. So the composite laminate theory analysis currently, again, mentioned it was running off the 54 millimeter test data, but as soon as we get the 76 millimeter and 98 millimeter test data in, we can update it with those new numbers and be able to validate again with a more flight-like tube. And again, the goal of the test plans here, we'll get more information on that as well, is to build all of the the test version of every single one of these critical sections of the vehicle and basically see where they fail at to validate that we're not going to have a shred in flight. But again, that work is going to be happening like essentially like probably in depth, hitting the ground running like tomorrow, Friday, and then sort of next week. The big one, again, Josh will talk about this. So the structure stuff has been the oven, but oven has been ovened in finally. So awesome there. But again, test readiness review. So essentially, I like to think it's more of an integrated test readiness review, because this whole period here and here is going to be essentially like full hands-on manufacturing and testing as much as the vehicle as possible. Basically, the test readiness review is going to be basically take a look at what have we done over the past month here, or past like 3 weeks, and say like, what are we looking at in terms of getting us towards putting a flight-like vehicle together, and basically making the full stack, putting like everything together for the flight airframe, and then testing it as a single unit. So again, that would ungate us to doing a lot of the more critical tests that will buy down risk. And again, we'll get to risk after this section, but things like ejection testing, doing radio testing, continuity testing of the wiring, and making sure that this vehicle is going to actually be able to succeed in flight. So again, that will be conducted in the wake of all this testing here. So we've got the avionics paper testing, full-scale airframe testing beginning soon, and then reviewing the propulsion testing. And we're aiming, I believe, for the actual full-scale test fire to happen later on in April, right next to the mission readiness review. But we will have a lot of data informing like how that's progressing up at that point that we'll be able to roll up in here. And the propulsion system as well. It's being designed to be able to kind of be plug and play into the rocket as much as possible. So we're very lucky that it's not gating a lot of the other milestones. The big one that does gate a lot of things is getting the structures together so it can actually have the rocket and do all these tests. And then mission readiness review. So essentially, once we've got the flight vehicle put together, gone through all the paces, we've already had the results of our destructive testing campaigns. Now we can start doing injection testing, loading the bays up, doing tolerance testing, doing slot testing, and basically saying does this thing look like it's ready to fly? Do we need to apply extra reinforcements? Based off of the results of the test data. And then again, kind of going at logistical concerns here. This is mainly focused on the manufacturing and test methodology. I think we'll at the end have our section on logistics. That'll be a lot of the work that's going in the mission readiness review as well. And then that gives us about 2 weeks between mission readiness review and the flight. So travel, again, we'll get into this later, but we're leaving Oklahoma on April 17th, and our flight date is April 20th, and we're returning back on April 22nd. So that's kind of the high level overview of that's what the schedule looks like. And again, I got some test critical milestones there. So I already mentioned a lot of these, but full scale vehicle test campaign completion is set for March 24th. So essentially that's like the date that we will have already had basically made a section of every part of the rocket, destructively tested it, been able to do the 76, 98 millimeter characterization, and be able to redo that analysis for the TRR or integrated test readiness review. Again, full bay avionics testing. So we have the designs there. There was a little bit more work to be done on those, very minor things though, but essentially starting printing those, putting them together, turning them on, seeing checking continuity, checking the logic is operating how we want it to, and the stuff with the accelerometer-based camera, doing checkouts on that, as well as testing the recovery devices in isolation. We've already got experience with these Jim Jarvis style charge cannons in the past. We want to create the flight-like versions we'll be using and test those to ensure that they work with our fully integrated avionics system, or our independently created avionics system. And then, so flight like this here, power set for April 7th. Trey will talk a bit more on that. There's a lot of work being done up to that to ensure that we're on track for that. That's kind of one of the last gating milestones before launch is having our propellant ready to go. I'll talk about some of the risks there, and I'll talk about the kind of integrated risk assessment as well at the end. And then as well, the integrated flight airframe qualification that is set for our mission readiness review at April 7th, which basically means we have the rocket fully ready, tested, and hopefully only minor work needs to be done to get it from here to flight. And we'll talk about kind of the scheduling on that as well in terms of manufacturing direction. But that's kind of the high level overview of that, and we'll just move right on into a bit more detail with the airframe here. So, yeah.
Good evening, good evening, everyone. My name is David. I'm going to be covering a brief overview of the airframe manufacturing and testing. So airframe tube manufacturing, one development that we've had since PDR is the development of our contraption, which is an alternative filament winding source in addition to the X winder, which we've been using up to this point. It's about 90% operational. The other 10% is going to be firmware and power setup, which still remain. So we're excited to bring that online to hopefully increase our filament winding capacity. Components of manufacturing delays again due to the unfortunate DML oven outage, but that has been fixed this week, and we're excited to hit the ground running in preparation to do more airframe tube testing. Carson already covered it pretty well in the project schedule. We've done 54 millimeter airframe tube testing. We've learned the lessons. We've documented it in the Notion, and we're going to carry that forward into full scale testing in preparation for our test readiness review and meeting those deadlines. Risk mitigation and safety considerations for airframe manufacturing. One risk would be poor wind quality, jeopardizing vehicle performance, and reducing the airframe strength, allowing for too much slop at the joints. We're going to mitigate by adhering to filament winding standard operating procedures established by the club, and ensure that all members who are performing the winding understand the tolerances that are required for this vehicle to perform well. Another risk is damage to our filament winding sources, so the X winder and the contraption. We don't want these to become unusable, which would seriously jeopardize our chance of success. Mitigation, again, follow the SOPs, and if we suspect any problem along the way, just stop, evaluate, continue as needed. And of course, where appropriate, PPE, and ensure we all understand the risks associated. You'll recall from PDR that we introduced 3 ablative samples that we were preparing. Here they are, post-testing. We completed this just a few days after PDR. Again, just to reiterate, say different weight ratios of an epoxy, glass microsphere, and cork ablative material. We performed several test runs, including 10 and 20 seconds test runs with a propane torch. 90 seconds is, well, a special case for sample one. We observed a charred surface finish with no visible burn through in the carbon fiber plate, which we were happy to see, even after 90 seconds of testing. Some of the risk mitigation with this and safety considerations that we applied for this testing, and we also plan to carry forward into future tests as well. We observed a limited regression and a max back face temperature, which you can see a little bit of a snapshot of how we measured that here using a thermal camera of about 143 degrees C with the longest test run for sample one of 90 seconds, which does not exceed the high temp epoxy max operating temperature. So again, preliminary tests, we're planning to carry this forward and scale up a little bit more and apply it specifically to the nose cone. Gloves and respirator were used by our test conductor during the testing. We cleared the area downwind, fire extinguisher was on site just in case anything went horribly wrong. Future test objectives, determine the best application method of this ablative coating to the nose cone, which is going to be our most critical area to protect. We need to do some experimentation and development in that area. And then also we need to verify that the thermal protection is adequate at the design thickness that we're going to be applying the ablative material, the surface finish as well, and that it is able to handle the more extreme heating that was discussed earlier.
Yeah, so a big thing we were looking at on the structure side of things was how long would it take us if it was worst case scenario, pedal to the metal, all hands on deck to get all of the structural components for one full rocket out the door and fully post-processed for final assembly. So identified our critical path with single vehicle assembly, or sorry, single vehicle manufacturing was going to be our filament wound parts. This is mostly due to the fact that our outsourced labor historically has had very good, very quick turnarounds with those aluminum parts, and that our bulkhead or flat plate material can be produced in large quantities. So from this basic Gantt chart, you can see that a full airframe, again, all hands on deck, working around the clock, should be able to be manufactured and post-processed for assembly in around 3 days. Here I've got them color-coded based on what mandrels they're using, so which components will block which other components. So for instance, these two green ones are both using 76 millimeter mandrels, which we only have one of, so they'll have to be done sequentially in that manner. Here, the light-colored cells are to denote hands-on work, so either filament winding or post-processing, and the dark ones are cure time, so that would be using the other. So yeah. And then to kind of give an overview or a closer overview of Structure's timeline to launch. Again, this is something that Carson was covering on one of those previous slides, but we're going to begin that full-scale airframe manufacturing and nose cone manufacturing ASAP. Obviously, delays being what they were, we were hoping to be able to have our test campaign almost fully completed by now. But it was just simply not a possibility due to the oven installation, but that has been installed as of yesterday, from what I've been hearing. So you should be able to hit the ground running on that. I think 10 a.m. tomorrow is when we're starting. And then our primary objective for our first few initial lines is going to be getting a full, at least mock-up airframe ready for our reveal event on March 14th. That Ray's been helping us coordinate. And then finally, our final component production is set to begin following comprehensive test results from our test campaign around March 24th. So that still gives us plenty of time. Thankfully, we adopted a very conservative schedule on the outset of this project. And so we'll still have plenty of time to complete this testing campaign fully and get started on production.
Yeah, with the propulsion manufacturing testing, I'm going to try to go through this quick. The static test fires for propellant characterization, that takes 3 days, one for casting, one for assembly, one for testing. We can imagine that we can get our final propellant characterized in 3 days, which will start tomorrow. Testing is normal for the head-end ignition system verification, even though we've switched to propellant shavings, we'd still like to have a full system test. And then, yeah, system of a hot fire with the full 7613,000 motor. Carson mentioned April 7th, but we're going to go ahead and give us a couple days lead time by setting our goal for April 3rd. Risk mitigation. So the forward enclosure pressure limit, we've done a lot of testing on that, on what we would need, and it's dependent upon the casing threads. We have some backup slides and all these risk mitigations. By the way, if you'd like more information, we have empirical validation of erosive burning margins, which would be comparing data to previous research, and also in-house research with the 54-2800 test that we did, also to other outside sources of data. Phenolic liner bonding reliability, we've been giving the exact methods given by the manufacturer of this case, but we will do a testing campaign and evaluate that at a smaller scale before moving up. Also, backup motor casing plan. We have two 76-13,000 cases on hand, one planned for test, one for flight. In the case that both of those fail, we will have a fallback to a 76-8000 commercial motor, which I think Landon might mention that we've run some calculations on that to make sure that that would still be okay. So manufacturing plan and finalization in terms of what needs to be manufactured. The performance bounding narrowed our possible nozzle dimensions enough to where we can confidently purchase our base nozzle and get those machined. The HEI compatible threaded forged closure. We've got all of our stock material and our design is finalized, so we are ready to get our invoice to start machining those.
So for avionics manufacturing and testing, as avionics, we don't have too much manufacturing. Our bays are all 3D printed. So we're currently making the final design changes on those, and we should be able to start actually just 3D print them, test them. There's a lot of off-the-shelf parts we're buying for this, putting together some, a lot of assembly. We do have a lot of testing for our cameras. One is looking at battery times. We want to look at how long are they going to last, and in real life testing how long they're going to last, and how hot it's going to get. We have large batteries. We have a lot of components. We want to see if that exceeds how much heat these run cams can take. And we've done some battery testing with a 9-volt. Joey did some calculations on how long this circuit would last with 9-volt, and we were within 5 minutes. So we're pretty confident that for our battery selection, we can predict what that's going to be. We'll get those batteries in and test them to make sure. We need to do a lot of activation testing. In the sustainer, we have a solid state relay that connects to the ADA latching relay to turn on our two run cams in our sustainer. So we need to actually test that from a distance. Can we connect with the K3 and actually activate our cameras from that distance? Additionally, we have our accelerometer system, which I talked about before, but it detects changes in velocity, and we have a lot of components which we can show in the backup slides, a full circuit layout of what that's going to be. Additionally, we wanted to do G-force camera testing. If there's a single point of failure for all our cameras, it's probably going to be G-forces on the run cams. And we would like to be able to stick those in a centrifuge and see if that has any effect on the reporting. And additionally, we need to do ejection manufacturing testing. We currently don't have that much experience as a sub team in manufacturing these. So we need to practice and get more consistent at making those. And additionally, just doing that water igniter testing and move into full ejection testing. That's going to be sometime late March, early April, when all the when structures has tubes made that we can test with that, because we have to test if we add a little extra friction, add a little extra weight into our stages, if that's going to affect how well our ejection testers work. I have a little picture there. We're using like a brass tube, sort of like a cannon, putting gunpowder and some wadding into it with epoxy on top. That's the general makeup of our ejection charges. And then just generally, we have to check our flight computers that their sensors are working properly. We check telemetrum, the barometers, accelerators, every sensor on all of these flight computers. We to ensure they're working properly before we actually launch.
And one thing is I'm trying to real quick here, as far as the cameras that I think it might have fallen through in terms of we touched on it, but just to like make it really clear. So we've got the 3 camera activation methods. We have
that is the next slide.
Oh, it's the next slide. Okay,
Yes.
Next jump right into. Okay, awesome. All right, I'll let y'all cover that then.
Yeah. So, but real fast. My name is Joey. I'm one of the guys that was working on all the cameras, and I'm going to really quickly run through our timeline and then also talk about the actual camera designs. So as far as avionics is concerned, right after CDR, we're going to go ahead and do all of our updates and make sure we have all of our procurements in, because we do have a lot of off-the-shelf products that we are using for these circuit designs and for the actual avionics components. By the 8th, we're going to go ahead and get started with 3D printing. We're going to actually do our weight testing and our charge testing on all of our materials and make sure that those actually meet the criteria that we need them to for launch. By the 9th, we're going to make sure we have everything assembled so we can actually start testing our accelerometer power distribution system, make sure that that is functioning correctly for the booster. By the 13th, we're going to actually make sure and get started on doing a full sustainer and booster avionics and camera bay testing and assembly. By the week of the 24th, we're going to get started on doing our ejection testing and our full bay testing, making sure that everything comes together. The ejection charges work, cameras work, avionics bays are fully functioning, ready to go. The week of the 31st, we're going to get started and hopefully get everything done for programming the Kate as far as getting the sustainer working and making sure that it can actually eject all of the charges, make sure that it can actually target the cameras and start recording. And we're going to continue anything extra with assembly and testing that we need to do for that week. The week of April 7th will be our final build and assembly week to make sure we are flight ready by the 13th of April. And as far as the cameras are concerned, because we do have a big issue with the reliability for our cameras, which is why we have 3 different designs. So our first design, this is going to be our primary design that's going in the sustainer. This is our solid state relay that is on the Kate 3 that will fire a latch relay to start recording the camera. Cool thing about this is that we can actually dictate when this is started remotely via the Kate's receiver. This will give us the highest likelihood and reliability of capturing every aspect of the flight itself, from ignition to launch to recovery. Design 2, this is the kind of research section that Jacob designed. That is our accelerometer design. So microcontroller is actually going to be reading when the accelerometer detects a change in velocity. When that change occurs, the microcontroller is going to send a signal to start the run cam. And this is going to be a very self-sufficient system. Once it's turned on, we don't have to do anything else. We let the microcontroller do the work for us. The only thing to note is that there is going to be a slight intrinsic delay due to the nature of this circuit. So we might miss the first, like Landon said, second or so of the initial launch, but we will get everything, including a guarantee for recovery being documented. The last design we call the R control group, because this is just, we turn the camera on and it just runs. This one will manually need to turn on right before launch. If it's too early, then the batteries could potentially drain, but this circuit's going to last just about between 2.5 hours. So not really an issue there. But once this is on, this is guaranteed to control or to record every aspect to the flight. So between these 3 designs, everything regarding the flight should be covered.
And now going into risk analysis and mitigation. So we've kind of sprinkled this out throughout the presentation, but a big focus again from PDR to CDR is kind of like, you know, dotting our I's, crossing our T's, and making sure that this vehicle, like when it gets on the rail or the tower, is going to have a successful flight. And a big part of that we've even started work on over the past like week or so is risk analysis, identification, and mitigation. So I'll just jump right into the section here. This is kind of a really big slide, but I'm going to talk through kind of our project risk identification and tracking like setup. So we're using a 5x5 risk tracking matrix, essentially going through all these subsection, all the sub-teams, focus work areas of the rocket, and kind of identifying like what are the critical risks, emphasizing things that are like extremely critical to the success of the flight. Could result in loss of vehicle or failure to light sustainer. And so I could run through these real quick, but essentially goes 1 to 5 in terms of probability, 1 to 5 in terms of impact, with 5 being the loss of vehicle or definitely halting the project. And then for reference on the major objectives here, these are from PDR, but again, design, manufacture, launch, recover, 2-stage high-altitude rocket reaching altitude 50 kilometers. So, and then tying into that to validate designs for future vehicles, basically with the goal of the space shot. So anything that kind of like impacts those directly are kind of major objective items there. And then going into minor objectives, those are things that like we really want to have, like cameras kind of ties into that. And so again, we've gone through bunch of different possible risks. And again, this work is kind of like really in its preliminary phase. The goal here is to have this much more well integrated by TRR. And I'll talk about it a little bit more on the next slide. But essentially going through all the possible failure modes and figuring out how we're going to get these from critical or medium risk items down to low risk items in time for flight, and how we're doing that through our mitigation, which I'll talk about now. And so again, this is a work in progress thing. From this last chart, here's some of our like key identified like red risks that we're tracking internally. So essentially, our risk mitigation strategy right now is to identify risks right here that pose a significant threat to recovering the vehicle, having successful flight, or achieving our major objectives. And then ranking these by the ones that are, like, we see as like being probable or having like a moderate likelihood to occur, and then running through each of them systematically and figuring out how we are mitigating these risks through our schedule. So I have here again the list of some of the key objectives here. And I'm used to running through these because we've kind of talked about a lot of this already. But as far as a specific example here is the airframe structural failure risk, how we're going to go through like this kind of is retrospectively, but like risk identification, our subscale structural testing, and also speaking to some rocketry experts or people who have a lot of experience, like figuring out like how they would deal with the issues that we raised here, and kind of going into our initial airframe reinforcement setup. So really beefing up these critical sections of the vehicle, and then hopefully we're going to buy this risk all the way down with our actual like physical scale testing. So again, this is kind of the preliminary work that's been done for this. I go into current issues right now with this. We're using an external tool called Risky Project to track all this, which unfortunately is not like coupled directly into our project management tracking database we use on Notion. We're currently trying to figure the best way that we can like get this to be like the same across them, as opposed to having like you need to have someone check out the file every single time and update all this. Or if they need to do that, at least having it all in a centralized place where we can have these risks being tracked independently by our teams, and as like mitigations get implemented, tracking like how they're being brought down, and then using this tool potentially as just a visualization aid here. But yeah, let me see anything else here. I think I talked through most of it. Yeah, but essentially the big focus is to have a lot more on this by test readiness review, be able to go through these risks you see here and show how we've bought each of them down individually, and how we are planning to continually buy them down until we deem them safe enough for launch, and ensure the entire vehicle is ready for launch for our mission readiness review as well. Yeah, that's kind of a brief look at the risk identification mitigation we've been doing over the past week or two, and then I'll go right into operations logistics with Mr.
All right. I'm John Pippin. I'm the logistics lead, and I'm going to talk you through our plan for getting there and launching the rocket. So here's our launch procedures and SOPs. And so on your left, there's a brief overview of our plan. In Stillwater, we plan to practice a lot. We only have one shot at this launch, and so we want to make sure that everyone knows exactly what they need to do, when they need to do it, to make sure that we can reliably get that rocket on the rail safely and in a timely manner. And we're going to pack everything. We have a list going. We're going to make sure we're bringing double, triple mission essential equipment, make sure everything's packed safely, and that nothing is going to get damaged during transport. The night before in the Airbnb, we're going to do motor assembly, a final weather check just to make sure that cloud coverage looks good, it's not going to rain, and then final full stack test, make sure that avionics, there's good readings on all the charges, charge terminals, yes. The morning of, we're going to do a surface finish, and we're going to do that final assembly to make sure we're ready. Right before is loading the launch tower and arming the flight computers. And then after is GPS tracking, recovery, and then cleanup of campsite. And on your left, you can see a brief description of 8 different positions. The reason it's 8 is because the Zinc Center has sponsored 8 people to go. So that's the worst case scenario, assuming we can only bring 8 people. And then we have a little comic about the range danger operator. We don't have one of those.
Yeah.
Yes, important. But let's talk a bit about our travel plan. So the plan is to leave on the 17th and go to the midway point in Gallup, New Mexico, and have an Airbnb there. And then Friday, drive the rest of the way to California and stay in an Airbnb somewhere around FAR, just so we're not having to go immediately into launch after 2 10-hour days of traveling. So we'll have a day before our launch to prepare everything. And then that Saturday, when we feel ready, we're going to go to the FAR site, and we're allowed to camp out there. So we'll be ready in the morning when our window opens. And then that Sunday, we're going to launch. That's our window from 8 a.m. to 3 p.m. And then once we do recovery, we're going to clean up and head back to the Airbnb for the night. Hopefully very successful. Monday, we're going to drive back to the midway point and stay at another Airbnb. And then Tuesday, make it all the way home. And we'll have 1 to 3 passenger vehicles and at least 1 truck with a trailer. And for the motor pool vehicles, they need a OSU student employee to drive them. So we'll have 4 so people can take in shifts because drivers will be in shifts of no more than 4 hours to make sure no one gets too tired while driving. So let's talk about the far side itself. So we're using their launch tower. It's a Newman 20-foot. It's similar to the one we were developing, and all it requires us to bring, besides the rocket, is a 3 to 4 inch C-clamp. So recovery, everyone will go into a bunker, and every rocket that has motors powerful enough that you need to do a bunker call, we'll watch them all go up, and then once FAR gives the all clear, we can go out and use our trackers to find our rocket, get our bearings, find our rockets. And there are dirt roads out in FAR to help you get closer to the rocket, but we'll likely need to hike a bit. The weather in April, there's a wide range of temperatures. There's lows as low as 40 degrees Fahrenheit and highs as high as 90 degrees Fahrenheit. And the winds are moderate. Camping is allowed the night before, and there are some site hazards, including wildlife, such as scorpions, spiders, and snakes. And there's also protected wildlife. FAR is home to the desert tortoise, which is a protected species. As covered before, the Mojave has extreme ranges in temperatures. So it'll be really important that everyone brings multiple layers so they're ready for whatever the desert throws at them. And also to drink plenty of water to make sure no one gets dehydrated. And then our travel cost for the group of 8 people, you can see how we've broken it all down, but for a group of 8 people, it comes out to around $5,000. And for a maximum group of 20 people, it comes out to around $11,000.
That's the end of the main section of the presentation. And we're now ready to open the floor to questions and or answers.
Very good. So first, let's do a round of applause. Yeah, nice job. Yeah, I know we've run long. We're an hour and 40 minutes right now, but that's okay. It's an important project. We want to make sure we give it considerate time. We do have a couple of folks online, including Professor Farouk, some subject matter experts. I want to make sure we give time for Dr. Elliott to make some questions as well. Comments. I was very impressed with the presentation. It's one of the better presentations I've ever seen in terms of your delivery. I don't think there was a single presenter up there who was not clear, concise, presented really, really well. So very impressed. I assume you guys practiced. Very, very well done. I think it shows. So I'm very impressed with the presentation and everything you gave in terms of the graphics and stuff. So I'm going to hit my overview questions. I want to make sure I give plenty of time for the other experts that provide some questions in here. Let's talk about the risk, right? You have your known unknowns, and then of course your unknown unknowns. But what is your single biggest risk that you're concerned about?
So, I mean, we can go back. I can go a bit more detail into our the current analysis we conducted right here. With these are our critical risk for tracking. So I can just go through these right now. So the biggest ones in terms of like critically impacted success are obviously like flight failures, and then a close second are things that like significantly delay or like prevent the launch from happening. But going through this list here, let's see, airframe structural failure. So that's like a typical like shred you see. This is a very high performance rocket. This is something that we'll kind of go into the mitigation plan here. It ties into that, but essentially, one of the big reasons for us reducing acceleration between PDR and CDR is kind of cognizant of this versus some of the other like critical airframe loading things, like those come as well. Another big one that we're looking at right now with like airframe production is the mandrels. We are a little bit better about this now because we've got some kind of backup methods to get these things prepared. But a large part of the first part of this semester was spent getting these manuals prepared. And we had some issues in terms of like procurement. And so one of the risks we're identifying, as we mentioned, is we only have like one of these mandrels for our like critical diameters in stock. And so potentially if we were to have a line that we're able to like salvage the mandrel out of, that could set us back by quite a bit of like a week plus to get a new one of those in. And so in terms of mitigation for that, again, like following procedures is like a really big one. Weighing our options in terms of like looking into parallel with the testing, like get more of these critical mandrels. Standard motor ignition failure. This one is not like a results in like destruction of the rocket, obviously, because we in our comps like a plan for the case where the standard motor is not light and the vehicle goes up to a much lower apogee. But in terms of our project objectives, it really does hurt us. The kind of issue there is that with the switch from the head-end ignition system that used the copper thermite down now to using ammonium propellant shavings. The copper thermite system is basically like almost like guaranteed. Like this thing, like once you ignite it, like it's the reason it's so dangerous, so volatile is because when it gets ignited, it goes. Versus the ammonium propellant, it's a lot more susceptible to pressure. And one of the big issues there is like the pressure you can have like in the case as you go like up to like 29,000 or I think like 19,000 feet trying to light this thing. And the big one is that we can't really test this on the ground. Like we can do ground testing, obviously, of like a static motor, but that's not going to give us like what happens when you've got like 19,000 feet in the air, you're going close to Mach 2, like can this thing still light? And that's just something we're not going to be able to know. And we're going to do as much testing, trying to validate with like online sources as we can to increase the odds of that as much as possible. But that's another thing we're tracking there. Nose cone thermal failure. This is.
Well, and I think your 5 through 9 are pretty straightforward from that standpoint.
Okay.
So we'll come back to the nose cone thermal piece a bit, but let's talk about the sustainer motor a little bit more. So is that the biggest issue or the biggest concern? Is the ignition failure, or is it really just because you are dealing with a custom motor, and so you deal with a lot of unknowns and concerns?
I would say so. Trey, if you want to talk about like kind of the known. Like knowns that we've got, like in terms of mitigating.
Yeah, the biggest risk obviously would be a catastrophic failure during launch. And there's several things that could cause that. For example, if there was erosive burning that wasn't simulated, and so obviously we're tackling that by doing an altogether test several weeks ahead of time. So if there was something that if our analysis was off, or anything like that, then we'd be able to address it within those weeks leading up to launch.
We do have the second flight case that we.
Yes, we do have a second flight case. If there was an issue during the test, another example could be the phenolic failure. And so again, that's a lot of these like big issues are addressed with that altogether test that would occur April 3rd through April 7th, that window.
And one thing, like we are tracking that. I think if we go onto the like previous slide, the master list here under propulsion, we do have like the 4 closure failure from electron liner. These ones are like already addressed. We see them as much less likely because like already going through that testing campaign, we'll have the opportunity to bring that likelihood way down and like with the full like scale.
So these aren't necessarily the current ones, or these are hopeful.
This is prior to mitigation.
Okay.
Prior to mitigation.
So these haven't been mitigated yet.
Yes, so prior to mitigation, but like keeping in mind, like keeping cognizant, like it's kind of like a bit of a compromise because like these haven't mitigated yet, but the probability is kind of affected by like how easy the mitigation is going to be. So like in terms of things like the motor like having like a structural like failure, like a pressure failure in the forward closure, liner failure, these are things that are going to be with our test campaign like proven. So we rated them in terms of our initial like identifications lower, and they'll go even lower like once those tests have been like conducted.
Okay.
Well,
after we get through those gates, I'm gonna be able to come back and reevaluate.
Yeah.
There's one thing, and I don't want to go back to the slide because I do want to come back to some of the modeling validation components, particularly the Monte Carlo components. Go in a little more bit depth about how you did that later. We're not going to do that here. But also as you're going through the process of refining and getting to know your subsystems and your rocket better, continually, improve those verifications in the simulation so that you know what you're getting. You'll be able to refine that. At the end of the day, if you keep doing that really, really well, you should be able to pinpoint and get your targets. For those that are online and want to ask questions, please raise your hand. And before we do that, I'll turn it over to you.
And do we have like a speaker set up for us?
Yeah, I'll do that on mine.
Okay.
Here if we need to.
Yes, first thing, what do we have? Nose cone's gonna be made out of fiberglass, is that correct?
Yes.
And that's so you maintain connectivity. with
Yes, RPM facility is the concern there. And also keeping in mind, there will be the leading tip aluminum, stepped aluminum piece that inserts into there as well to handle like that tipped heating. This is something that, Josh, I guess if you want to talk a little bit more about that. I think it's kind of a standard, as far as like our rocketry, construction setup.
Yeah, it's a very sort of tried and true method. It's not one that we've adopted ourselves, but it's all one that has been.
Well, you guys are making from scratch. We've used.
Yes, yes. But it's one that's been very well documented and used on very similar projects. One advantage of that is just due to the geometry of the part, we're planning to use like a 3-inch fiberglass sleeve. So it is actually a continuously reinforced part. A lot of the times with hand layups like that, you'll see some sort of seam. But with that sleeve approach, it will be continuously reinforced, which obviously that's a lot of structural.
Okay, and if you lose connectivity with the Kate, can you possibly reacquire it later? And is that sending you GPS location of the rocket to hopefully give you the location when it lands?
So that's actually one of the risks we're tracking here. We've been looking into our like reference flights. One of the amazing things about the Kate system is that it has been used on a lot of high performance rockets already. We mentioned Mesos is one, but there's plenty of other examples of flights that have used the Kate system. And they one of the really cool things is they have their blog where and hopefully we'll be able to contribute to it, where successful flights using the Kate system are published to like they publish their flight data, publish their like build specifications, and so you can see like how they were able to operate in the specific airframe. We've been looking at reference airframes that have a similar kind of layout or a system to us, where we have like the fiberglass nose cone tip. I want to see. Can you use slide number on the I can just start going back. But as far as the construction of the nose cone, one of the big considerations for how it's designed is the transmitter is located all the way up in the front there, about as close to this forward. It's kind of cut off, but there's going to be the aluminum tip up here. You keep like 1.5 inch minimum distance from this, but essentially the benefit here is that your carbon section is going to start, I guess, yeah, right here. So you get this entire kind of like hemispherical load where you're able to get this omnidirectional signal out. So where you're being included is very small. We've already, we covered this in PDR. We did range testing of this exact transmitter in a very similar setup. I don't believe we had the internal decomer related. It's also fiberglass coupler here as well. We had a very similar flight-like setup that was taken out to Mount Scott, and we did range testing up to like 51, 52 kilometers. Is that correct?
Yes.
Okay, so we've already validated, and again, with higher atmospheric pressure, because this thing will be going up. But the system is flight proven, a heritage on very similar rocket projects to ours, and we've actually gone and done our own testing to validate that within this setup very similar to this, that we'll be able to get the range that's required. But that is a very critical thing. Like if we do lose that GPS, it's going to be very hard to impossible to find this thing. So that's one of the risks that we're tracking there. Yeah.
And you mentioned that you're gluing the phenolic liner together, and that's recommended by the.
Yeah, I'll look great.
Yes, so the 7613,000 case is manufactured by Loki. It's run by a guy named Scott. So we stay in contact with Scott quite a bit. The 7613,000 case is one of the few cases where you actually have to do this. And so he has developed his own tried and true method of bonding phenolic liners together. We have step-by-step instructions, SOPs, to follow for this. And so we're going to do some smaller test campaigning during the same time as we're doing our propellant characterization to verify on a smaller scale. And then we'll obviously move up with that as we go towards the full hot fire.
Okay. Yeah, that seems like a probably critical.
We actually do have
The backup slide, it's way down there, but
I can go find it.
Shot it works.
Do you know, can you
It's like 90.
get a slide?
It's like 98 or something.
98?
Yeah, it's way down.
Can someone give me a number?
Next. There we go. So this is kind of like a summary of his exact.
But you haven't done this yet.
No.
Okay, so obviously it's one of the first station.
Yes.
So
Yes,
anything
that's.
that you haven't done or didn't have experience.
Yes, and that is in our plan to do like within this week.
Okay, that's good for me.
And let's go online. All right, so. Go ahead. I think Josh was first.
I joined late a little bit, but would you be able to go back to your motor sim slide that you just passed? I just wanted to look at it.
Oh,
Chris can ask his
that's
question
another
as you-
backup slide, right? Let me see. Was it this one? So the lower and upper bound. Do you want to start with this one?
Yeah, what if there's like specific question?
I didn't have a question. I just wanted to look at it for a little bit. So you can go to Chris and I'll just stare at this.
Yeah, Josh just likes to look at motor simulation. That's first. This is jam. All right, Chris, you want to go?
Yeah, okay, so I'll start with one that's not propulsion related. What is your shock cord material? Are you guys using?
I think we're using the ripstop Kevlar, was the
Kevlar?
baseline for that, unless we made any changes. I don't think we put it on the slide though, but that's the current baseline, yeah.
Okay, and then have you guys verified that you're able to pack down your chutes and your shock cord down to the space requirements that you're giving yourself?
Yeah, so that is one of the things that we had done in between PDR and CDR was really trying to size the recovery volumes. And on the Fruity Shoots website, they have a weight listed and also like a packing density. So the reported volume is 0.18 ounces per cubic inch. That's using a packing bag or a deployment bag. We could use that, or we could size it based off the traditional like Z-fold method, and that is a slightly lower density of 0.13 ounces per inches cubed. So we just basically use that density and our volume or in the mass of the parachute to figure out how much like length in the rocket needed to be dedicated to that. But that is another test that we want to do is actually procure these parachutes and then verify that they will fit.
That's one of the important ones with vehicle integration. Is like we already mentioned, like the ejection testing, but even like kind of hand in hand with that is like the fit testing with all the recovery devices and making sure that they fit, don't cinch, and like doing your recovery test obviously with them installed, because you can get a pretty significant increase in interface friction there when you put these in. So that's something we're considering kind of our procedures for doing these the integrated vehicle testing. If that answers your question.
Yeah, that answers it. So now moving over to propulsion related questions. So you earlier, I guess this slide right here kind of says a little bit too, your lower bound propellant and your upper bound propellant. And you'd mentioned your, kind of using an upper bound with the risky Batman. So you guys are planning on going through the full characterization process for the propellant you end up using, right?
Yes, actually starting tomorrow.
Okay. And then what is your plan on getting that to a acceptable pourability level?
So basically what we're doing is we're taking our base CS propellant and we're basically increasing the dispersion between the particulate sizes, and we're doing that by increasing the aluminum content and decreasing the 200 micron content.
Is there a backup slide with the calculator?
That's true. Yeah.
Can someone give me a number or
It's wrong way.
99.
Here we go.
And so we've been able to develop this propellant calculator that we can input our desired motor geometries and our desired ratios of propellant ingredients, and it will ensure that our like things such as like the cure index and things like that are within desired range. So we can know a little bit more about the how it's going to cure and the pourability and things of that nature. But we also it's worth mentioning that we feel comfortable with increasing the aluminum content because it's already our base propellant has a very low metals percentage, and so we have quite a bit of margin to play with there.
And do you recall there's the paper that this was based off of? Do you know the author of that or?
To John DeMar.
Yes, DeMar. Okay, I was just wondering in case they were.
Thanks, John.
Yeah. That's what this at least the liquids pourability aspect of this sheet's based off of is that paper by DeMar.
Okay, and then you guys are planning on using that same propellant formula for both the booster and sustainer?
You answer that. I was saying, yeah, we're using a commercial booster, so this is only for the sustainer.
Okay. Okay, so that answers my next question. What is that? I must have missed that. What is your booster commercial motor that you're using?
Yeah, I'll go back.
Yeah, it's the OP500X. Oh, we've got a little slide back over here. Yeah, but it's Aerotech OP500 XPS. Did I pass it? Yeah. Whoops. There we go. Yeah. But yeah, this is a workhorse of a motor, very high initial like thrust. That's very good for application because it's gonna. We really do not have to worry at all about making sure that we're stable off the rail. This thing's got a really like big kick to it initially. We've also got club heritage with this motor. We've flown it prior on Arachne, which was our successful flight to just under 26,000 feet out at Argonia, which was designed for the Spaceport America 30,000 foot COTS category. And so we're familiar with, this is another kind of thing here, but as far as like operations concerns, like getting this thing ready the day before launch, we've already conducted this, and a lot of members of the capstone team have hands-on experience with preparing this motor before. So that's a big consideration as to why it was chosen. But yeah, does that answer your question there?
Yeah, that answers it. I think my last question I've got for you guys is on your staging slide, you have a 10-second your booster burnout between 10 seconds and 30 seconds or time, that very last bullet point there. Have you guys considered reducing that? And then kind of as part of this, like, what is your stability at this point in flight?
So yeah, we can answer all those questions there. So the first one I'll tell you is we've been looking a lot into justifying this particular decision for that 10-second coast. Again, we've already mentioned Mesos as far as the interstage design change we did. Mesos is honestly like a very, very similar rocket to this design, going to 293,000 feet as opposed to our projected 188,000 feet. Accomplishing that by using long burn duration motors, but a huge part of that was they did a 17-second coast with a very similar aspect ratio, very similar weight vehicle as the one that we're doing. And so essentially, like, we have that kind of like reference justification that this is a rocket that uses a very similar design that we do that has done a almost twice as long coast. But yeah, going into your stability concerns, we have I'll hand it over to Landon, but if you want to go back.
Yeah, so specifically about the 10-second delay, I don't think I have it on here, but just from looking at the flight simulations, I know that our velocity at the sustainer ignition is right around Mach 1. So decreasing that, if we decrease the time, we're basically going to hit a higher, we're going to be starting out faster, so we're going to hit a higher Mach loading, lower in the atmosphere, which is going to hurt us on the thermal range. And then our sustainer ignition is actually right here on the 14-second mark, and then it burns for about 3 to 4 seconds. So that we start at a stability of like 4.5, and we end at a stability of 3 during our sustainer burn. So the changing the ignition timing doesn't change that hugely, but we do have a good margin above the 2.0.
Another big consideration I'll jump in there is that we're staying above. I think our minimum speed we drop down to during sustainer coast with the 10-second coast is like Mach 1.1.
Yeah.
So we're staying above like the nastiest part of the transonic regime that would add a lot of extra drag and like weird stability we have to watch out for. So yeah, that's like tying into this analysis as well, kind of our justification for that, if that helps answer your question.
Yeah, that looks good.
Could you repeat that? I would be.
Yeah, you guys are good.
You said good.
Okay, awesome, cool.
Okay. Do we have anyone else online?
Can I jump in again? Are you tracking with a Yagi or how do you?
Yeah, I don't know if we have a picture of so there's two separate devices. Yeah, so, and this is kind of a bit more of an operational thing with the telemetrums. But the K3 comes with it's sold as a package, so it comes with the actual transmitter module. And it also comes with a transceiver. And it's a punky device. It's the same one we conducted the 50-kilometer downrange testing with. Do you know anyone from Avionics have a picture of that in one of the slides? We just look and see if it's on backup. We could like Google it right now.
I assume that, well, you're not gonna be able to see the rocket the whole flight, I assume. So how are you gonna track with it? Or is it automated or are you just?
So the tracking on it, it's not automated, but it does actually have voice commands with it that give you feedback on the location. So with the GPS pings, it stores that last ping in the transmitter itself. So at least if you do lose your GPS, you will have the last recorded data in your hands. And the other thing too is in our experience with the testing, I did not have a clear visual line of sight on the rocket at the time when we had it in the fiberglass nose cone with the carbon fiber tube, but I still was able to quite easily pick up a lot by having a rough idea of where it was. So the sensitivity on it is, in our experience, wasn't as high as we thought.
In terms of like
Directional. Yes.
which means the sensitivity to the Yagi is very high. In terms of like picking the up. But yeah.
Is there any way to improve that? Like, it seems like, hopefully you kind of can guess where it is, but if you can't, then.
Yeah, theoretically, like you could look into like designing a ground station that is essentially automating what we're doing, like, because this will be a handheld thing, like if someone is going to be dedicated to like tracking this on like during the flight. We've got a lot of experience at the club with the other system we mentioned, the Alpha Spectrum Telemetrums. We're not going to be able to use their tracking capabilities, unfortunately, due to the carbon, like they're fully enclosed in carbon fiber. But they have a very similar system, and I think we might have lost service. They also have the redundant falconry trackers, which are using a separate Yagi. Those are attached to the shock cordage of the vehicle. So once the deployment occurs, they'll free those. They're basically just like little RF like beepers. We have a separate set of Yagis that are able to pick those up and give us a bearing on them. So we can do a triangulation to figure out like where, like a coordinate of where those are. And again, the booster's going much lower than the sustainer, so it's a much easier kind of recovery. Very much close for the launch pad. But yeah, going back to like the experience, those metrums that the club has used very extensively have the same kind of setup where like you're hand holding this thing and you basically it's beeping out telling you like your exact bearing and how far off you are. And again, you have, as far as like trying to visualize like your error, like as long as your cone is at like plus or minus like 15 degrees of where the vehicle actually is, you will be strong enough to get a signal. And again, it's guiding you the entire time, telling you like rough elevation, rough bearing, and if you're like starting to get off or not. And again, if you lose the vehicle, you should be able to like sweep back and forth in like a last known area to find it. But as far as again, Mesos, they went to like almost double, like 1.3 times more than what we were going to. That was a hand tracked using the Kate transceiver. So we're not too concerned about that, but we are tracking as a risk.
We have anyone else in here? Like, you guys want to ask questions?
So my questions are probably mostly for Josh in manufacturing, especially when it comes to airframe. You outlined a critical path for like 3 days, all hands on deck. What is all hands on deck?
So that would be
What number is that?
all hands of the structures team, if they're willing to work 9 to 5. Obviously, we're gonna have a lot of extra hands from the design team.
Yeah,
whose work will be pretty much completed at this stage of the project. Obviously, there's a few small items they're tracking, but nothing major. And so they've expressed an intent for wanting to get involved with the hands-on stuff. So yeah, I mean, at the end of the day, if it comes down to it, we could probably get 20 people in there if we need to. If it's like the difference between getting a rocket made or not. But with the timeline we've given ourselves, this will include just the structures team plus people.
Yeah, so this is enough to operate like both lines continuously. And also have people, I guess like there's some downtime here as well, but basically enough people on each of these tubes or each like the nose cone part be able to sand it down, but don't do a lathe off and I'd say lathe off, it's really putting on the lathe and just sanding it smooth on the internal external surfaces. But having enough people, we've been able to do like solo line operations, especially like some of the automation we've implemented on that. So yeah, this really could be fully accomplished by the structures team, but if there is additional hands needed, especially like in terms of like simultaneous like assembly tasks going on, so like getting these things staged as the rest of the vehicles put together, like the entire team can pitch in there.
I appreciate this as an exercise, right? But you have to be cautious with this because this doesn't consider
Yeah.
finish and integration concerns.
Yeah, it's definitely.
Again, assumes best case scenario.
Now, this is why I would be very careful to say, like, this is just components and post-processing to get it ready for assembly. Obviously, assembly will take, X number of days in its own way, but this is from a structured perspective, all of the components we need.
What is that, like, close to 172 man hours technically?
A lot,
Which
yeah.
is not exactly feasible for you guys. So, because I only asked that question due to the fact that structures has a high risk. So how many of your members are ready to run lathe, they're ready to run on the X-winder and contraption? All of them, or?
So that was a huge part, and we mentioned this in our PDR pretty heavily. Some of the big stuff we did early on was like all hands winds on one of the closed competition rockets. So I'm pretty confident in my team. Obviously, they can probably speak to it better, but in their ability to run the X-winder. I know I think every one of us has done at least 2 or 3 filament winds from start to finish.
And also another thing is we have enough members that like theoretically we have like a single person like in charge of the wind off and like a few hands helping out. They have the level of knowledge to be able to instruct and like, make sure things are going correctly. And also you said like 102 hours doesn't seem feasible with capstone. I've seen it. I've the 1,000-yard stare. I've seen.
I know, I would advise against it. It's very unhealthy.
Yeah. Well, and another important thing is like those dark shaded cells is carrying power. So that's just down the hands off. You're just waiting for it. So
Yeah. Okay. And then the other thing on interstage, since you ran FEA and you have a material selected, is that going to be made in-house?
we haven't studied yet. Obviously, our number one option is just using Shorty's machine shop that we've had good experiences with here. It's really a matter of our confidence in the machine shop.
And it's like it's a relatively simple lathe.
Yeah. I haven't talked to anyone on our team yet that is confident enough in their lathe abilities to manufacture that part. So right now our intention is to outsource.
Okay. And you've got enough lead time then? Okay.
Yeah, typically turnaround from Shorty's on the mandrels was 2 or 3 days at the most. He is very quick.
Yeah, I mean, some of that geometry is a bit complex for a lathe operation. So I do see that being possibly a CNC lathe operation, which I'm not 100% sure Shorty's has.
Yes.
So that was my question too about outsourced labor with a quick turnaround. You'd call that out. How reliant do you think you're going to be on that if you need to? Because you have 4 weeks.
Yeah, I mean, ideally now that this design is finalized, this is one of the parts along with the head and ignition, our fins, we're going to get in contact with the staff. So even if it's not a possibility with them, we can go look at some other options.
Okay.
So again, not too really worried about that being something that sets us back.
Yeah.
Obviously it doesn't have to detract you. You're correct to raise concern about it.
Yeah, I didn't know if you had identified any other machine shops. The DML does have a CNC lathe, but we don't have a high level of confidence on that.
Okay.
So we're getting there.
Yeah.
I will mention that propulsion team has reached out to Shorty, and obviously we won't know until we get the part back, but he has claimed that he's able to machine it.
Which for reference, that is, whoops, I skipped past it. This part right there.
Okay.
But he has claimed that he can do it, so I guess we won't know until he does it, but.
Yeah, I mean,
Yeah, my only other question was lying within logistics. So John, you said 4 OSU student employees.
Yes.
Have you identified who those are?
So me, Elba, Trader, one right, and then we need one other. I've not identified the one other.
Okay. Because that you have to be, I'm sure all of you are over 21.
Yes.
To do that. And then also the cost associated with that, just so you know, 3 vehicles is going to be close to $5,000.
Yes,
The motor pool loves us.
Yeah, because they charge by day and by mile. And then you get charged for your gas card. So
I wish they would charge by opening the door too. So every time you get in a vehicle,
just something to be aware of. Yeah, I think the $5,000 8-person plan is a bit optimistic. We've sent teams to Arlington for $7,000 through Motor Pool.
Okay.
The truck is $90 a day, 80 cents a mile. So something to think about.
Yes, we kind of, if people are willing to use personal vehicles where we can, just, and then have like few motors will be.
And yeah, that's another thing I think we might have glossed over. So as far as the logistics planning, I think our contingency is the 8-person case. We're essentially like Zink's like committed being able to bring 8 people out there. With FAR, they have a hard limit of 20 members. That's like including spectators, everyone affiliated with the rocket. So we're gonna be able to bring, and again, we have a 24-person team. So we're only able to bring 20 people out. And so part of the work we're going to be doing in the next few weeks is identifying like who these 20 people are, and kind of like where we need subject matter experts. Additionally, people like who might be like other students who are not on the team that we want to bring in, based on like obviously want to give team members as much priority as possible if we want everyone to get out there, but kind of like weighing like who we need out there, just to have like the most benefit to like getting this project like a successful launch. But yeah, we've been planning for like the 8-person contingency. I just wanted to mention the FAR hard limit is 20 people. That's another thing we're planning around the operations.
The other way to consider this is a 15-passenger van. It's someone will have to go through training through OSU, but again, that's a $90 a day and probably about 80 cents a mile. So very expensive. So something to consider.
Yeah. I'm glad we have a contact who's very well aware of.
We do it all the time. So I think those are all of my questions.
Yeah, the big one I had was so your fin attachment and your fin analysis. So your fillets are leading edges, right? And your fin leading edges are also to be considered an area of the air beam. Have you all done calculations on what that air beam looks like on those fins, and especially the fillets and what epoxy you're going to use to attach that?
That is something that we're looking into. That's a good point. I think right now we're baselining one of the those like structural epoxies you're looking for in terms of like the I know we're doing a lot of research like in the wake of like the Proline discovery. There's a bunch of other options out there. I think we have one of those baseline, but didn't put it here. I can't recall off the top of my head what it was. But in terms of like making sure that the epoxy does it, and there is like a front part where it is a leading edge around like where the actual kind of like scoop portion happens. It no longer is leading edge, but looking into like if we need to apply some of our latest coating there to ensure that the epoxy can reach like up to its glass transition temperature, and also like in terms of like oversizing it to make sure we have plenty of margin there. That's a good consideration.
And it's also something that we pulled from reference vehicles. Looking at reference vehicles, many of them have flown in similar flight regimes with either aluminum fins or aluminum shielding on the fins. So it's not, it's like you said, something we're tracking, something we're paying attention to, but it's not like a major concern.
So my main concern would be the fillet thing. It looks like it'll have plenty of safety margin on the actual fins, but did y'all take into consideration that the aluminum would be not quite as strong as it's heated?
Yeah, so that's kind of part of the reason why we upped the thickness. Like for reference, like the Project Mesos vehicle, that was like a 0.165 thickness fin, and it went to like similar Mach number as us. That was on their sustainer, so we are thicker than that. And I believe on theirs they also did like a tip to tip like carbon attachment over their fillets, and that's something that we're going to look at doing as well. Just so it's not just the actual one line of epoxy holding it on.
Just like,
and then he sanded down the hexagonal like pointy part again. So
getting as much material on that as possible is like
and then booster tracking is that just the RF tracker?
So right now, essentially the plan is doing very similar to what the capstan team last year did. I believe unless this got changed, we still have the bottom exposed coupler on that booster there, the non-load bearing section, keeping it fiberglass. So theoretically, once the vehicle's on the ground, or I guess theoretically, when that separation charge pops out, there's now an exposed fiberglass section. And I think we're looking into the placement, because right now on the sled diagram, I think these ones are they're centrally placed, so we can again move these up and down to make sure to try to get these the metriums as much into that volume as possible. And the big one is they have the whip antenna and the omnidirectional antenna, kind of choosing between those. This would be a good case where you can kind of send the whip antenna or omni up into that fiberglass volume. But essentially with that, we're looking at doing a kind of similar approach to what last year the capstone team did, where the primary what we're basing off of just having is that falconry tracker. We're looking into if we can get a second one of those Yagi's able to pick up that frequency, like a 233 megahertz frequency of that tracker. So we could basically like from the launch site, send a vehicle out, have a read from one direction, have a read from a second direction and triangulate, like get like a rough set of coordinates where we think it's going to be. And like, if we need to do like more sets of like triangulation, to figure out where it's going to be, like we could just like do more and more lines, try to like refine that. But hopefully they had success with that. Again, they were going much lower, but we do have the kind of advantage of the terrain far. Again, it's like out kind of in the desert. So there's a bit of micro terrain. So there's going to be like kind of bumps and divots, but versus like Argonia, Kansas, it's still pretty flat, but there are some slight hills, like major terrain that happens, where you can get obstructed. In terms of your sightlines to your vehicle, there's not a lot of that out at far, especially like within the landing range of the booster. So we should have a pretty kind of clear shot to find it. So we're not like too worried about it, but it is a thing we're tracking. Yeah.
Yeah, I would definitely, this is 30,000 feet altitude, right?
No,
For the booster, it's 15, and it really brings it. I mean, it really brings it down the open end of the interstage. So, I think, yeah, the tracking on that is something we're tracking.
And something we're looking into as far as like ground testing would be, I mentioned this, so I kind of forgot to finish my train of thought there. With that exposed coupler, with the fiberglass, we were looking into, we were talking to some of the people from Castle last year to see if they had any experience with this. But we heard from them that it's not feasible to like get a lock with, at least with the Metrums, like once it's in flight. Because they tried that very same method, where they had the fiberglass coupler section, they had the Yagis down in there, and we're aiming them at the rocket. When it popped out, they weren't able to get any reading off of that. We're looking to potentially seeing if, like, once the vehicle settles on the ground, if there's like directionality where like you might be able to just get a sync, because all we need is a single GPS ping to be able to like know exactly where this thing is. So if we're able to get a single signal like received by a Yagi, that would also help. Like, so basically doing our like first pass search with like the falconry tracker, like triangulation, knowing a rough area to search, and like keeping the Yagi for the Metrums out to see if we could get a single ping. Because once we get that ping, we know exactly where it's going to be to go pick it up. It's kind of like our general plan. Right now, we're baselining just having that falconry tracker triangulation. We're talking with the FAR people to make sure that we don't have to worry about any other flights out there using the same frequencies. Because that'd kind of be a nightmare if we had like two sets of beeps happening. And you don't have to worry about, like, if you point the freaking Yagi the wrong direction and you have beeps as well. So imagine like having 4 sets of beeps to figure out which one's real, or which one's real, which is yours. But yeah, so we've got a bit of experience. Like, that method worked, again, obviously with a much smaller altitude vehicle. So there's precedent, but it's a risk. So I don't believe they did triangulation. They just used single line there. But big part of our cargo will be figuring out like how to do that very fast and efficiently, because we don't want to like be fiddling around for like 3 hours. Like, okay, like here's my line, here's your line, where do you think the thing is?
Yeah, are you gonna have a falconry tracker on the booster as well?
Yeah, so your booster, I think sustainer, we were baselining having one on there as like another redundancy, but we're going to primarily rely on the Kate. But it's assuming it kind of going in that if the Kate, something goes wrong with its downlink, we do have at least one other system to be able to locate that and make sure those are on different frequencies. So again, we're getting these by ourselves, but yeah.
Okay. And then just one other thing, kind of timing wise, looking at your schedule, like if you have what, from 3 p.m. until sunset to find it in theory, at the worst case scenario, to find the rocket. What do you do if you can't find it that first day?
Yeah, that was a good thing to think about. I guess in terms of like trip planning, that's something you have to consider. It's like you're going to try to like book extra days of like travel and Airbnbs. That will drive up the cost significantly. I do know one big thing about FAR is like it's a community of Rocketeers. Worst case, if like the vehicle is out there and we can't find it, it's kind of like Argonia, where like you're not gonna have people like out there looking for it for you every single day. But if someone stumbles across it, and you write your little name in Sharpie on the inside, they will bring it back and like get it back to you. We'll get it eventually. Hopefully get it eventually. Unless it lands on a turtle, then we're gonna have the police coming in and arresting us.
But I mean, another conversation we're gonna have as we like talk about who's going, you know, what cars are we taking, and like who's going on their own dollar. I know me personally, like a lot of us are like intense, you know, paying our own way, and especially for like camping out there. You know, we might be able to stay behind, but again, it depends what far.
Well, I think if you give yourself, you know, that backup option of having one vehicle or one team be able to save the next day, right?
Yeah.
You know. If you don't find it that second day, you're probably not gonna find it.
And again, it's something we need to look into FAR, what FAR regulates as well,
Yeah.
because they're very strict about like who's
Sure.
out there and how many people.
Mhm.
So they might be like, hey, if you can't find it, you can't come back. Like you said.
Well, the main thing is they control the site. They don't control anything other than the site, like being out in the desert around the site is totally fine. It just like, if we were to stay like on to Monday, like their launch schedule right now, is they're doing this, the Saturday, Sunday, or Friday, Saturday, Sunday. So unless someone else had like, or like they were planning another event for that Monday, there wouldn't be anyone out there. So obviously that means we can like go into their site because they lock the gates and stuff, but then like, we're still gonna be out to, like, it's public land out there. So, or like, some of it's public, but yeah, it's like on mostly unoccupied land. So there would be like and again, like the FAR, this is like the bulk of the FAR facility, like they have the like reaction research society area up here, and they have like the launch area down here in the bunkers. But like, that's really it. This is like in the middle of like a 20 like kilometer radius area of like basically nothing. There's a few mountain ranges, and then we're looking at like prevailing winds a little bit. Oh, I forgot to mention, we kind of talked about this briefly on the ConOps here. The reason we've increased the sustainer main deployment altitude, and this is something that's like prone to a little bit of future work, but we're like doing this conservatively right now, just like foolproof it. But essentially, the reason this went from 2,000 to 5,000 is, believe it or not, there are mountain ranges that are near FAR, the southeast and northwest ranges respectively, I forget the exact names, but that are 3,000 AGL above the launch site altitude of 2,000, like 28 or 2,080 ASL. So essentially, and this is an AGL reference altitude here. Basically, we want to give ourselves 2,000-foot margin for the parachute to deploy no matter what, because again, we've had experience rockets where you deploy the main to 2,000 feet, and then nothing's happening. And then like the last few hundred feet before it's the ground, you see that main beautifully unfurl and it saves the day. So that's kind of what we're baking in terms of like main deployment. But like if this comes down over one of those mountain ranges, and again, they're not like, it's not like the Himalayas, like these all have roads going up and around them. It's very common for people who fly it far if they end up in the mountains, like to recover. There's a bit of a concern there, I guess, with the I guess eventual recovery. It's mostly flat land with that exception. Benefit those, it gives you a high point to kind of look down on the surrounding area in terms of like recovery. But if we do end up landing in the mountain, we've accounted for that on the sustainer. The booster, I don't believe, is going far enough to like warrant that. It should be able to go to either of those mountain ranges. The sustainer definitely could, though. So,
And I would like to see that from your Monte Carlo simulation, so you have some at least predictive analysis about where your likely landing locations are going to be at. And then we'll help you at least, target all these decisions in a more analytical fashion.
especially like building a model that we can like update like day before and basically say like, don't be launched with this.
Get the winds,
Yeah.
wins aloft are, and you say, okay, now we have 90% probability that we're in this region. So,
yeah.
So I had one final question. How many total cameras do you have?
4. Yeah. So 2 sustainer, 2 booster, and they're all looking. This is a change from PDR, but they are now all looking side facing.
Okay.
So we're getting, and this I can talk a little bit more about the total sustainer like redesign we did with the bay there. But yeah, big consideration was like we want to have at least 2 cameras that are capturing like the money shot view of like us going to our apogee and deploying like everything. And we see like even though we have like down facing, want to see the recovery. Typically what happens like when your nose cone or like when your main volume opens up and that just takes tension, it will kind of like send it flying so you'll like be able to see back into like the booster. And we have the 2 cameras either side so you can get that like, or they might be not quite opposite, but like close enough to get 60 degrees or sorry, 120 degrees. Yeah. So covering most of the field of view. And these are again wide angle field of view drone cameras that we're using for these, the RunCam Split 4. So we should get some pretty cool views from woods.
Yeah, good. That's important. We have to hear
The K3 also records audio from the flight as well.
Oh, good.
Oh, I didn't know that. That's cool.
And so you should have that through the entire flight, even the cameras are.
I don't know about that.
The calculations for the runtime for the cameras are on, I think, slide 94 as well.
Yeah.
I think that's
Well, and I think this goes back to your decision. You're talking about the different options to trigger them. So my highest launch was on a Terry Orion 4 out in Wallops, and you had a camera that was triggered by the acceleration. And so, while you see, most of the flight goes up to 87 miles, you can see that, and all the way down until it lands in the Atlantic, you missed that launch. And so, you're even just like half a second and you're coming off that rail so quick. Man, having that, design 1 or 3 as an option for this. Anyway, it's something you guys should think about, figure out at some point.
But yeah, so we'll have that. So going to that, so we have the 2 cameras, this approach, going into both on the sustainer, kind of the operations for that. But the last thing we'll do, like right before flight, is that shunt on the igniter to check continuity, basically like make sure this thing's ready to go, and we'll have like cleared the pad by this point. And then we can send our command to enable the camera to start recording, and then send it. And so we'll have that on the sustainer. Booster, we have the accelerometer camera, and we also have the turn on and leave one. The reason we put this on the booster, again, just kind of like this simplifies this whole system if these are running off the same like method, and it's already a pretty high reliability method. We have this control here just in case. Hopefully, if this fails, we have like a known control, and we'll have at least some of the flight footage. Unfortunately, not the coolest stuff in the sustainer, but this is again low risk. At least we're getting it right now. But that's the risk here is the kind of operational concern of like we have to turn this on before we do final like igniter checks and clear the pad. And if there's like a delay with like weather, like a stray plane or something, this could be on the pad. I think this is a concern Josh Anderson raised to PDR for like multiple hours. Yeah. And so we're sizing this based off I think like 2-hour battery. I think they have the backup like 2.5 hours for this one. So yeah, so we can have this one on for a while. But if we go over that, there is a point where we have to look into kind of the altimetrums as well, because these are also turned on and leave the screw switches. So there's a point where like data about the boosters running out of avionics battery, which we have to like take the vehicle down and recharge or replace batteries and put it back up. But we're trying to make sure that those times are like not super like wide like variance between all these things. So we have like a known window for like how long can be like armed, everything ready to go on the rail before our final like igniter check and launch. So we don't have to worry about like if the camera's like a 30-minute battery time and then the like chart like the computers have like a 2.5 hour having a mismatch there means like you'd replace one and then like you'd run into like another 2 hours and you have to replace those the booster batteries. It's a whole mess. But basically we're tracking like a 2.5 hour time for all of this, the electronics on the booster, so we can like have a considerable amount of margin and just like wait on the pad for anything to get cleared out.
No, that sounds good. I have a whole bunch of other notes I've taken. They're mainly comments and they're not really concerns.
Okay.
Questions, and so we'll kind of go through the stuff later. I think, I think with our 2.5 hour runtime, probably just go ahead and close things out.
All right.
So,
and do you want to do like a final call for questions? I saw Tyler raise his hand.
Just a quick comment on this. While we're talking about cameras, we've already got to be up by the nose cone to, start our gate. It might be a good idea to do a turn on and leave up in the nose cone as well. That way we have diversified system to both our sustainer and booster. That's the minor.
Yeah, that is I guess that is worth considering. So yeah, there's the distinction between the arm, like the turning on of the gate and the final like arming and like of the motor.
Activated by the handheld trains.
I know, but what if the SSR for whatever reason doesn't work?
Yeah, and that's the other thing we want to mitigate.
Systems guarantee both of our sustainer and booster.
That's one of the things we're looking into mitigating with like the full avionics stack.
It seems like a lot of thought and that's not this. It's one minor thing that we do not a lot of that.
well, it's already just testing things, right? And one thing you did, right? So you have a TRR and MRR, right? You should have half a dozen TRRs. Every subsystem on here, you're going to have a test readiness review for that, particularly when you come up with propulsion, avionics, your structures testing, your ejection charges, all those things. If you test it, you should have TRRs as part of that. So you have one MRR, but you're gonna have a lot of TRRs. So make sure you're keeping your schedule updated with the process. So, all right. Nice job, everybody. Again, appreciate that staying so late and going through this. It was a good presentation. Look forward to see how things go from here. So now that you're done at 7:30 at night, you can head straight back to the DML and start.
Yeah.
That's what I'm saying.